Quit, sorry. Okay, take two.
Hello, everyone. My name is Nahum from the Aerospace Corporation, and I'm part of the AIAA local, I guess, chapter. And we hold a mini conference just like that every June, as close as possible to Asteroid Day. I'm going to talk about it a little bit later. It's in commemoration of the asteroid.
What is Asteroid Day?
Asteroid Day is an organization that was created after the Tunguska events to advocate for the topic, to do outreach.
I thought you meant it was this particular day in June.
There is.
Oh.
There is.
What is Asteroid Day?
Asteroid Day is
June 7th?
30th.
30th. Okay.
June 30th
I learned
is
something.
officially Asteroid Day, but because we cannot hold events on this particular day, we hold things in proximity to this, which is one of these. And I've been involved with this at Aerospace for probably about 19 years now, to different levels, doing STEM, conferences, some studies, and trying to increase the community of people who are involved with asteroids. But we'll talk about it a little bit later. And I think for now, thank you very much for inviting us today here, and looking forward to hear.
Okay. Some people want, they can sit in the front, then it will look like there's people in the room, for those who are not here. Okay, so I'm going to now share, right?
Yes.
I can figure out how to do that. Is it? You had it set up, so why? Here we go. Oh, sorry, share screen. Desktop 2.
Yeah. All right, it's coming up.
Right there, it's working?
Yeah.
Is there a way to turn off the lights?
Yes, so, yep. Leave one on in the back. And, yeah, let's leave it like that. I think that looks good. Okay. So, welcome everybody again. As Alan mentioned, I also would prefer this to be informal as much as possible. So let's see if I can get rid of this. Hide the controls. Hide floating meeting controls. There we go. Yes. So please, we had a little bit of an introduction already, but I wasn't sure what exactly. So I'm going to give a little bit more introductory material. But anything I say that you want to just pick up on and ask, it's fine. I mean, we're here to communicate, right? So all right. So you've seen the meteorites. 99% of all the meteorites in the world, and almost that much of the ones in that room, are samples of asteroids. All right. So that we have some meteorites that we know are from the moon. We have other meteorites, perhaps 100, a little more, that we think are from Mars. And that's it. We have no meteorites from Venus or Mercury, or we don't think we have any from the outer solar system at all. All right. So, and this is a conference about asteroids. So I'm going to talk about, in fact, a mission from the Japanese Space Agency called Hayabusa 2, which I was very peripherally, I was not very involved directly, all right? But I'm sort of a little bit aware of it, and it's very topical because the first papers are just coming out, in fact, literally last week. So I thought I'd talk a little bit about this as because this Hayabusa 2 mission went to this asteroid called Ryugu, you see spinning here, and it brought back some of that material. And so I'll say very briefly a little bit of what we've learned about that, and I'll try to also say, well, why? Why would you do this? Why? What else could you do? And there's an American mission, the NASA-sponsored mission called OSIRIS-REx, which is going to another asteroid, which we think is largely similar. We won't be sure exactly until we look at the stuff. But that has also sampled some of that and is on its way back to the Earth. So we're in a new era, right? So we have one of the first sort of ideas to get across. We have 99%, we have 60,000 meteorites in captivity, as I like to say. 99 point something percent of them are from asteroids, right? But almost none of them come with a little stamp that says made in this asteroid at, assembled at 3.2 AU and a date, right? None of that happens, right? So we don't know where these things come from. Now we have an opportunity. We're going to some asteroids and getting some samples and bringing them back. And comparing to meteorites is obviously an important part of that. So in a way, this is like, we were just in a geology building, right? So this is like putting meteorites in context by doing the geologic field work, right? We have these things that are out of context and we're trying to put some context on them. So Alan already talked a lot about some, gave us a good introduction about some of this. So just wanted to reiterate a few things about, why does he and why do we study these weird rocks that fall out of the sky? It's kind of a strange thing if you think about it. And we're doing it because we want to understand how planets are made and how this solar system was put together. That's our fundamental thing, which the impact hazard thing is a different thing, right? And mostly is concerned with larger impacts. So much as seismologists only can, pay their mortgage because we have earthquakes, but earthquakes hurt people, right? But no, actually buildings hurt people. Earthquakes tell you about the Earth, right? Same thing here. Meteorites tell you about space. And yeah, these large impacts are potentially, very, very hazardous for a society, but that's not what we're talking about here. But so we want to address this issue of how do you take an interstellar cloud of gas and dust and turn it into a planetary system. And if you look at our system, which we don't know if it's completely typical, or in fact, it's probably not, but that's another story. We can see, that what we tend to think of as the solar system is really the dregs, right? Everything's in the sun, the first approximation. Alan said this, and everything that's not in the sun, almost all of it's in Jupiter, right? Jupiter has more than half of the remaining mass. But if you look at this, and this is our solar system, the 8 planets of our solar system, arranged in this is to scale by size, not by distance, obviously. But, you can see that you've got, some sort of a dichotomy here. You've got the terrestrial planets that are mostly rock and metal. You have the Jovian planets that are made of the most abundant elements, hydrogen and helium. Of course, they have everything else in them too, in there too. And so something's going on, right? Very fundamental to create this kind of a thing in our solar system. And we think that one of the important aspects, this is an artist rendition, right, is that as this is accreting, obviously it's getting hot in the center. Interstellar space is cold. There's somewhere in this accretion disk where the temperatures drop low enough that abundant volatiles can condense. So we call this the frost line or the snow line. You can have different ones. I like this because somebody did a nicer drawing than I can do, so I pinched that off the web. But the point is, there's a lot of this stuff. So once you can get ice condensing on grains, then you can grow things big enough. And if you're going to make a planet like Jupiter with 330 Earth masses, you got to grow big and eat fast, because the disk of gas is not going to last more than a few million years. And so those planets that are the gas giants had to acquire their mass when there was enough material around, right? And so the snow line is very interesting, but we also know, it's another schematic, is that in between the inner part with the rocky planets and the outer part with the gaseous planets, we have the asteroid belt, right? So this snow line, it moves during the process of accretion, but at least transiently, it was in the region where the asteroids came together. Sometimes we anthropomorphize this, and I was going to say we're born, right? Well, rocks aren't born, but you know what I mean. Okay, so the asteroids are a key component. I'm not going to talk about comets today. To understand how this process of planet building happens. And if you go to the Minor Planet Center, as I did back in 2013 for some reason, you can see that we track, thousands and thousands and hundreds of thousands of these things, right? And so here on this particular day, October 29th, the Earth was here. Jupiter's the big J up there. Here's Mars, Mars's orbit. And you see all the green dots, right, that form a band here. These are the main asteroid belt. You also see the red dots that on those, on that particular day, these are asteroids that are interior of the orbit of Mars and Earth, in some cases Venus, not too many inside of Mercury. And these are these near Earth objects that you guys are concerned with for potential hazards, right? But even these ones spend most of their existence out here, right? Because they're on elliptical orbits. So, so these asteroids are these small objects. There's millions of them, right? So, and these are very interesting to us. Oh, okay, I forget sometimes many of these slides have been repurposed for other talks, right? So I forget sometimes what's going to appear. But when I talked to, I think it was 2 years ago, but I can't tell time anymore since we started wearing these things. I haven't had COVID, but somehow I can smell, but I can't tell time. So I think it was 2 years ago. But if you told me it was less, I'd believe you. I talked about the evidence that meteorites are from asteroids. So I'm not going to really go through all of that. I just briefly mentioned that, especially these days, when everything is filmed or videoed, right? So this is from February 2013. This is the dust trail over Siberia. This is the Chelyabinsk meteor that came in, and we have video sufficient that we can reconstruct the orbits of a fireball and then go find the rock and pick it up. And so we know that these meteorites, there's a couple dozen, and these are the orbits, right? Here's the orbit. I'm too close. I can't see even where the Earth is up here. Oh, here it is. It's this dark black one, right? So all of them intersect the Earth because obviously they're all on the Earth. And Chelyabinsk was this particular one, but you notice they all have aphelion out in the main asteroid belt. So meteorites are from asteroids. In the case of Chelyabinsk, pieces of this, the biggest piece, this came in February, right? So it's frozen in Siberia. No surprise there. 6 meter hole in the ice above some lake, and they dug it out sometime later after things warmed up. And there's a piece of this meteorite. If you were interested in the sort of impact parameters, I thought maybe this crowd would be. Maybe you've already all talked about this already. But this is the size of a school bus or something, 11,000 tons, and roughly 440 kilotons of TNT equivalent, about 20 atom bombs worth. All right, so this is the hazard part. Some people were hurt by flying glass, but I don't think anybody was killed, and undetected until entry. And the point is for this is that this is a piece of the rock that was recovered. It's what's called an ordinary chondrite. Ordinary because it's the most common type of meteorite to fall on the Earth. So I thought I'd try to put this in a little bit of perspective, okay? So what about the asteroids, right? So here are the 2 largest asteroids, Ceres and Vesta, compared to this thing that you know. So they're small, right? Ceres is a dwarf planet. All the others are not. They're asteroids. They're not necessarily round. And just briefly review the question in the very broad way. Okay, so if we have 60,000 pieces of asteroids, what have we learned about asteroids from that? And what have we learned about how the planets are put together? One of the things to appreciate, of course, is that in addition to those big ones, so here's Vesta again, there are millions of small ones, and we don't know a lot about them. We haven't visited that many, but there are some. And what we do know is that many of these appear to be what's called rubble piles. So you can see they've undergone, there's a violent history, huge impacts, covering a large fraction in some cases of these. You can see lots of evidence of these. And of course, some of these impacts are what nudge these things into resonances and orbits that can cross the Earth. So one question you could say is, well, since we have the meteorites, what does that say about the asteroids? And Alan already alluded to this to some extent, that, but he didn't say too much about the statistics. But the vast majority of meteorites that fall are what's called chondrites. These are the ones that were not melted. So 87% of the meteorites, if you take them and you polish them, right, and you look at them, so you see these little bright flecks. This is iron nickel metal that is mixed intimately with the rock. So if you melted this thing, as he said, the two melts are immiscible, they would separate, and the iron would drain out of here and go to the core. And we have some examples of that, right? But most of the time, they're not this way. And moreover, if you grind this up and measure its overall composition, you find out that it is the composition of the sun minus the hydrogen and helium and noble gases, but we don't care about those either. They don't make those. And they're very, very low abundance, right? So this is somehow a sample of that solar nebula. And so that's the main thing to think about for most asteroids and most meteorites, is they're not just in this interesting part of the solar system where the gross properties change from rocky to gaseous, from small to giant, right? They're also somehow representative of the time that the solar system, this is an artist's conception, looks something like this, right? As the big planets were starting to form. And the cool thing is, thanks to Jupiter, we can get pieces of things that are not just pieces of asteroids, but pieces of the epoch of planet formation before there was an Earth. So they're sent to the Earth, and we get these things. Of course, we also have, and you saw the big irons, we also have samples of asteroids which did melt and then underwent violent collisions, and their cores are exposed. So these are the iron meteorites. And moreover, we have samples that we think with pretty high likelihood, although there's some debate, that are samples of Vesta. All right, so this is a basalt. This is a melted rock. It's like a lava, right? And it's probably a piece of Vesta because somebody asked a question about spectroscopy. You can match it to Vesta pretty well. But I did want to make a point. You see this black top here. This part was melted on the way through the atmosphere. This is the so-called fusion crust of this. And of course, it's been broken off below that. So we think we have samples of this differentiated planetesimal Vesta here. But if we summarize this, then the main thing we learn from meteorites is from the chondrites, and that relates to this accretion disk that the solar nebula that was forming before the planets, from which the planets formed. And there are a lot of things that we could talk about, individual topics of this. We actually already talked a little bit about stardust in there, the formation processes and the timing of how planetary materials how this material becomes rocky planets. And a little bit also to keep in the back of your mind, the delivery of volatile material like water and organic matter to the rocky planets, which probably didn't accrete with very much of it. And that's important for the issue of life, of course. So those are some of the things, and I'd be happy to talk at more length with anybody about any of those topics. But I wanted to focus a little bit more on this kind of a question. Okay, that's what we can learn by studying meteorites, but what are things that we can't learn by studying meteorites? Even we have 60,000 of them, right? We don't, but they're in the world. Or phrased another way, why should you return samples from an asteroid? What else is it that you can learn? And there are a number of things that immediately come to mind, but I wrote them down to help focus our thinking on this. right? One is, I told you meteorites come from asteroids, but how representative? I mean, there's a lot of bias, right? Things have to get into Earth orbit, but not only that, they have to make it through this thick atmosphere and hit the ground and survive that we can recognize. So there's a biased population. How do the meteorites come to the Earth? This is more related to your hazard question. How does something from the asteroid belt, the main belt, turn into a near-Earth asteroid or a potentially hazardous asteroid? What are the orbital evolution characteristics, right? How long does it take? What are the effects? This is more getting to this issue of the volatiles and organics. If a meteorite hits the Earth and it's not found immediately, a lot of meteorites won't survive on the surface of the Earth for very long. There's too much oxygen here, there's rain, right? They will weather very quickly. They're out of equilibrium in a strong way. Also, meteorites have organic matter in them, but you know, you can't find anywhere on the surface of the Earth that isn't, quote, contaminated by life in some way, right? So so this is an issue, and wouldn't it be nice to be able to get something in space to address this? And finally, there's also the important issue we heard about the DART mission earlier. What is the nature of asteroidal surface evolution? What's the mass wasting? How did mass redistribute it? These things are rubber piles that are half empty. How does that work, right? We can't learn that from meteorites. I think I'm gonna come back to this. The only point here is, you know, you got some idea in the gallery, but there are lots of different kinds of meteorites. And is this a biased population? So you can try to compare the meteorites we have to astronomical spectra of asteroids. The problem is that these are so-called spectral classes. What's done is looked at reflected spectra in the near infrared. These spectra are sensitive only to the very surface, fraction of a millimeter of the surface, and they integrate over something, right? So there's some issues there, and what we can see is, like, for example, in the main belt, which is about here, the C class, which are very, very dark, and C might mean carbon rich, that's what we think, are the dominant class there. But there's this kind of a stratification in the asteroid belt that tells us something about how the solar system was put together. And you know, can we really understand all of that? So one of the things we have to recognize is that this is now just a little kind of cartoon of the surface of an asteroid, of the surface of any, it could be a moon, it is the moon. Any body in space that doesn't have an atmosphere to protect it is constantly interacting, right, with the energetic environment around it. So micrometeorites, cosmic rays, solar wind, thermal cycling, even photons can do things to alter the surface, right? So, and the issue is, again, if a piece of a surface of an asteroid gets liberated and it will come to the Earth as a meteorite, it's got to get through the atmosphere. And that loose regolith on the surface cannot do that. The outer part of all meteorites are melted down, you know, a fraction of a millimeter from ablation through the atmosphere, because they're coming in at, you know, 17 kilometers per second or something. So they make a big fireball, and you have this ablation. Let's see, when did I start? And how am I doing on time? Because I don't think I want to talk too much about asteroid families, but should have noticed, sorry, I should have known. The thing is, I had this running already before we started.
I think I have 5 or 6 more minutes.
Okay, so I'm just going to skip through this, all right? But there are families of asteroids. How the asteroids come to the Earth is important, right? How they get into Earth-crossing orbits. And we know we have these gaps. This is semi-major axis against inclination. And these gaps are dominated, right, by resonances with Jupiter, mostly. All right, but how long does it take for these things to get in? You can make simulations and models, but measurements are always better than models. That's my bias, okay? We can try with meteorites to see how long they were exposed to cosmic radiation, because the energies are sufficient to cause nuclear changes, and you can try to measure that. And you get what's called the cosmic ray exposure age with some considerable uncertainty. So in order to try to address some of these, the thing that you want to do, clearly, you can't do it all the time, but we really haven't done very much, is go out to an asteroid, get some of it and bring it back and compare it to the things that we have here. And this is what the Hayabusa 2 mission did. Hayabusa means Peregrine Falcon. And it went to this asteroid Ryugu. And this is an asteroid. It's about 1 kilometer across. I think I have some, I have some stats on here. It's an Earth-crossing asteroid in the Apollo group. It's a dark object, very low albedo of the spectral type CB, which is a very rare one. Its orbit is such that it's about 16 months, and it goes from just under an AU to 1.4. It's pretty close to the ecliptic, and it's a potentially hazardous asteroid, which, no, this is the decimal point. This gets to, this should be 0.23, so a quarter of the Earth-Moon distance. Sorry about that. So Japanese launched this spacecraft. It does some Earth flybys to catch up with it. It stayed with it for a year, studying a little bit more, studying the surface. Had a rendezvous, collected material. I'll show you some of that, and brought it back to the Earth. Came back in December of 2020. The goal was to collect not a lot, right? 100 milligrams. This was the cost of the mission, so it's very expensive material. Actually, NASA's cost was 4 or 5 times this, but they're bringing back more material. That's another issue. But they actually surpassed their goal by a factor of 50, which is great. In addition to sort of doing this ground truth, right? I'm not going to go through this whole thing, but I want to make a point that the moon is by far the extraterrestrial body that we know the most about. And the reason is we went there 6 times and we brought stuff back, and we're still studying that stuff 50 years later. And when you bring material back in the lab, you are not limited by any sort of engineering constraints on how much power or data rates or anything else that you have to do your experiment millions of miles away. You can replicate things, right? Because different labs can make the analyses. You can address questions that arise the way science always works over time, rather than questions that only arose when the proposal was written, right? And you can train new people. So let me just tell you a little bit about what Hayabusa 2 did. Okay, you can see the timeline here. It launched these really cute, sorry, they're very clever as well as being cute. Little robots that jumped around on the surface. So HIBO stood for Highly Intelligent Bouncing Observation Unit. And OWL was an observation unit with intelligent wheel locomotion. That's a bit of a stretched acronym, in my opinion. So the density of Ryugu is only 1.2, right? So low gravity environment, lots of pore space, lots of big voids. And here's an animation now. I'll show you the real thing of Hayabusa 2 coming up to Ryugu, studying, of course, it's getting a shape model, the gravity field, all of that. And they launch these little beacons here down onto the surface so they can navigate precisely there to get a sample. The sampling cone comes down, shoots a little bullet basically, and the debris that's kicked up is kicked up into a horn, like a sampling horn, and it goes into a little capture chamber. Okay, so they did that on one spot, and now they're trying to get the surface material. Now they're doing something that's really, really cool. I think they launched this thing. I forget what it's called, but you'll see it's impressive in a moment. They let that go, and then they get the hell out of there. Why is that? Why is that? They're going to go around, you can see, and use the asteroid itself as a shield. So they get over the horizon, because what's going to happen is this little guy is going to do this little Star Wars maneuver. It's going to shoot a little cannonball out there and make a crater so they can get, they didn't have a way to dig, right? They're getting subsurface material. They go back, they find it because they mapped the whole surface. Let go the other little beacon. And then they go down and get material from that got excavated from the explosion. So they get something that's at the surface and a mixture of things that were at the surface and things that were a little bit below the surface. So it all worked. It's very daring, I think. I'm not sure NASA would do it, but that's another comment.
What did the bouncing one do?
Here's a picture. It has a little camera. It's got some takes temperature measurements, and I'm not sure what else. But they just let it go, and it just bounces around until it doesn't do it anymore. But one of the things that you see is very rocky. It's not this fine-grained, sandy stuff, right? I'll just show you some other pictures from the sampling site. So they study this and figure out where they're going to go. Of course, they have all sorts of engineering safety constraints. They can't be bumping into things and damaging the solar panels and all this kind of stuff, right? But they, here's the target marker. I thought this was a movie. It is, but it's very slow in the beginning. Is it going? Yes. Okay, so it's a frame by frame thing. Then they pick it up, and you can see this is a touch and go maneuver. They fire that little pellet, debris comes up, and they capture some fraction of the debris. All hell breaks loose, right? So it's clear that you touched it. And what's not clear is what you got. That's hard to figure out. And so I'm sure there's a bit of angst associated with that. So it came back in December 2020 into the outback of Australia. They picked it up. There were all sorts of, believe it or not, COVID protocol that was delaying things, especially in and out of Japan. We were very tight with that. But then they can bring it back to this wonderful curation facility, keep the whole thing in vacuum. They can transfer it between all these instruments without it seeing the air, and then send it around the world for analysis. We got a little bit here. We got a couple little grains. And they wanted 100 milligrams. They got 5.5 grams. And these are in these different, this is in the surface, this is the deeper stuff. In these different chambers, the collected material, the material was up to a centimeter, some of the bigger grains. And you can do a lot. By modern analytical instrumentation, you can do a lot with this. And I'll just give you a very quick overview of what we found out. Many of the things are still coming out. So the elemental abundances of these grains are like the CI chondrites, which are the most sun-like samples we have, the most volatile rich meteorites. I'm not going to go into all detail on this. The CI chondrites match the sun the most closely. This is a log scale over 9 or 10 orders of magnitude. Curiously, the CI chondrites, and here I'm showing you a picture of one, they are very rare. They are only 0.5% of all the meteorites are CI chondrites, but they're in some sense are most important chemically. But it's very, very weird because they are not at all primitive material from the solar system in the sense that they've all been completely hydrated. They've been turned to clay, 99% clay carbonates. And that's what this thing is. The CI, the Ivuna is the eye of CI. It's the sort of archetype, if you will. This is a polished thin section of it. When we look at grains from Ryugu, we see lots and lots of carbonates. And we see magnetite, which is iron oxide. It's iron metal that's been oxidized. So this rock has had fluids coursing through it. And what's interesting is we can also use the carbonates in some cases to date when that happens. And it happened very early in the history of the solar system. So we're trying to piece together the history of this asteroid. It's a CI chondrite. Like I say, about 0.5% of all meteorites are that. And you can almost understand why. They're very friable. They're not very compact. They weren't melted. They really can't survive very easily coming into the Earth's orbit, Earth's atmosphere. So there's a bias there. There's a lot of work being done on this, but basically, because we can make this comparison directly, we're very confident about that. Here's some aspects I just copied out of an abstract of a paper that came out. This is the first big paper from it, came out in Science last week. So this is all very new stuff, but it's not embargoed, so I'm not breaking any rules. And you can see the temperature is fairly low temperature, so sort of, bath water kind of temperature. For a couple of million years, this number may change a little. I think it's lower. And probably amino acids have been found. Probably this thing has never been above 100 degrees C. So these are the kind of things we're looking at. We're trying to understand also the exposure ages of these, and accelerator mass spectrometry, things that are huge machines, will be able to measure that and try to understand the surface processes on this asteroid, which is clearly, it's kind of an escapee from the main belt. It's a fragment of something, right? That's reassembled into a rubble pile, but the individual particles in it formed at the beginning of the solar system, within a few million years of the beginning of the solar system, and remembers a lot of this history, although it's complicated. So I'm going to stop there. I went way over. I'm sorry. Apologize for that. But I don't know when I started, so I can't say how much over I went. But I'm happy to take a couple questions at least, and I'm hanging around after that. So yeah.
Yeah. So you talked about this object had water involved, and then you talk about a planetary core. So what are your thoughts? And I know it's kind of speculative, but does that mean that there were like other planets in the solar system early on that maybe got obliterated, or what's the current thinking?
So of the millions of asteroids that there are, the vast majority were never in a big planet. So the asteroid belt is not the result of the explosion of a big planet. How do we know? Because if you get big, you differentiate into an iron core, a mantle, and a crust, which is thin, which is what the Earth is. And 87% of the meteorites that fall are not that. Now, we do have some cores, right? And Vesta is differentiated, and Ceres is it's partially differentiated. It's more of a mud ice differentiation, we think, just based on the moment of inertia. But we don't have any samples, right? So these things probably accreted as small bodies, few kilometers, 10, maybe more, and it depends on really. If you I didn't really explain this very well. Alan alluded to aluminum 26, but the basic thing is, if you accrete too big too fast, you have too much radioactive heat, and when you get big, right, the volume to surface area is bigger, and you can't shed the heat. If you're small, right, you can shed the heat, and then you don't melt. But if you get too big, you melt. So there are things like that. And in fact, the current thinking is that Mars may be a planetary embryo. Mars and Earth probably different evolutionary paths. But that's getting on some tangent of a tangent. Sorry, I get excited about stuff like that. So, thank you. Sure. Okay. If other questions occur to you, please ask. But I think in the interest of time, I should invite Vasilis Angelopoulos up to tell us a little bit about what's going on.
I'll make up your time, so it's okay. Very short.
You want? This is a Mac.
I mean, a connector here, but.
Do you have
yeah.
HDMI?
slide, maybe you need to log in the.
Yeah, I don't know
Okay.
if that's gonna happen.
Sure.
Maybe we just take it from the
Camera.
camera.
I think I was calling into the Zoom session. earlier.
Oh, you were calling into the Zoom. Okay, so he has the Zoom.
I have the Zoom.
Okay.
Yeah, because this way people can see your
Yeah.
slide better. The camera is
How many people are online?
not that many. Let's see.
No, still, even if it's one, we'll honor them.
So Vasilis is a professor of space physics here. And unlike me, is a rocket scientist.
This is the rock science. So let me see.
You gonna bring up all my emails to you?
I have
I think that's safe.
Windows 7.
I think it's safe.
Oh, there we go. This will work when this thing stops. Close over. But to reconfigure the system to be Windows 10, more modern now.
Yeah,
Windows 7 is no longer allowed, in fact.
I know. That's a big headache for
And
us.
so, and with that will go Microsoft Outlook.
There you go.
Yeah.
There's the link. Okay.
Oh, I saw you signed in earlier. Yeah, accept.
I want to
I
make sure,
think you join as panelist.
my voice is off, my sound is off. Do we have a,
Yeah, we have the sound through here.
Yeah.
So you can disable your mic.
But I think
Join as panelist.
okay. You can. Feels kind of like we're in a maze. You can sort of see lots of connections, but how do you get to the end? You're in the cornfield.
so this will clear everything for you, so let's
Yeah.
Comes up.
go there. Not that one. This one.
Ah,
All right. Yeah, you all hear okay? And I trust the same for online. So thanks for the opportunity. It's great to see everybody here. I'll be short because it's more like a vision for the Institute. It's not the cool stuff that Kevin was talking about earlier, science, but I can talk about science too if you ask some questions about that. So I was asked to give an overview of what the Space Institute is. And I have to start by saying it's clear, it's not very clear to most people what it is, including the people who are actually putting it together. So it's
early days.
It's early days, but the concept is really good. Everybody, is signed up to it because we think it's the right time to do something of this kind. So space, what does space stand for? It stands for space, planetary, applications, communications, and engineering. So conveniently a backronym for things that we care about and we love. I'll just start right away with the mission and vision statement to set everybody, on the right concept. And the idea is that at UCLA, a lot of science, technology, and entrepreneurship related to space is already happening, but there's no sort of focal point in which people from across campus and across disciplines can come together and exchange ideas and find out about what each other is doing and then collaborate in order to do better and more interesting stuff that will be of more use to everybody and most importantly to the community and the world. Because after all, our mission at UCLA, as any public university, is to advance our knowledge for the benefit of humanity. How do we do that if we don't talk to each other efficiently? So the idea is to talk to each other more efficiently. The goal is to elevate space science, engineering, entrepreneurship for the benefit of humanity through interaction of fundamental research of space and from space, we're already doing. And encourage more of that. We study the sun, how the solar wind affects planets, including early planetary formation or today's space weather, the planets themselves, and how they're made up, what are their physical characteristics and their evolutionary history. Astrophysics, so evolution of the universe, cosmology, and the evolution of other galaxies and stars from far away, remotely sensed from space observations, Hubble and so on. But also look down from space to Earth observations, remote sensing, climate and weather. Study not just planets in our solar system, but exoplanets as well, and search for extraterrestrial life either here in our planetary system or at other planetary systems. All that we do already in some form or fashion, but we don't communicate efficiently. And with this center, we could actually create the scientific branch of this institute could actually coordinate itself through the institute to do better science and more unified science. But we also have the engineering, the School of Engineering that does technological innovations already funded by NASA, DOD, NSF and other agencies, but we don't talk to them very often. This is a forum that would provide this communication. And they facilitate activities in space that we use in our scientific exploration, but others can use in industry as well. Moreover, we teach students. Now, wouldn't it be better if those students actually participated in the scientific and technological breakthroughs that are made and participate and learn from that and feel the excitement of doing that and do more of it as they evolve in their careers at academia, research organizations, or industry. So providing a better educational environment for our students beyond the textbooks and problem sets to actual hardware experience is really key in modern age. We can actually look up everything on Google and Wikipedia. And one is the instructor, right? But putting it together into something really as a educational experience that stays for life takes some doing, and we would provide that doing. Communication with the public is hugely important in exciting the public about the exploration of space and innovation and technology, new technologies that are coming out of this, and bringing on, feeding the pipeline. Exciting that 5- and 6-year-old that walks into a space operations center that is operated by students and says, "Oh, one day I want to do that. Control my own satellite," and that will drive them for life, and bring them to eventually through K-12 to academia. And engage also the private space sector, because one of the most, actually the most important, the most coveted commodity and the limited factor in today's advancement in industry is not material and resources, but human resources. It's the lack of talent. There's not enough of them to populate the booming space sector today. This is where UCLA can help, and the Institute can help galvanize these connections and outward look to the industry and the public. The idea of forming an institute started actually from a proposal to revitalize our faculty. Back in the 40s, there were like 1940s, there were like 10 faculty members that studied space physics, a branch of space science, where we studied the sun's connection with the planets. And then that withered over the years until the last decade dropped down to 3. And so we took a look and said, the dean took a look and said, hey, do we just let it atrophy or do we actually put money into it because it's important and interesting? So in response to actually winning an NSF-funded faculty position at UCLA, he took a further look at it and said, now is the time. Either we go big on it or we just cut it off. And he solicited a self-review and an external review of our program. And from that, he learned that we need to actually go big, create an umbrella research organization, that's the institute, and hire 2 new ladder faculty, which is now done, and there is more coming, we hope, and create professional master's degree program to basically train people in industry in space-related stuff, space science and space engineering. And the reason for that is primarily shown here. The space activities over the last, it's about 2 decades, has been growing steadily, in fact, exponentially. And this is a rapid resurgence in space industry nowadays, which is mainly driven by the low access to space, a low cost access to space. So you've got 50,000 satellites by SpaceX, the new web, these new technologies, but also NASA and others are able to now do much more for less. And so it's really important that we recognize that this both technical and scientific riches have yet to are still coming, many more are coming, and it's time to invest in this rapidly growing endeavor. This is the basic reason, and some more reasons here is the space economy, which is currently about $500 billion a year, is projected by 2040 to go 1 to 3 trillion a year. And so it's really a huge industry that is growing by leaps and bounds. Now, why UCLA? It's unique in its space science. Over many, many decades since the dawn of the space age, it has had the space program. It is very diverse in terms of space is actually practiced across multiple departments. Just like space missions or space industry is also diverse. It really takes talent from many different disciplines to make it work. UCLA is a magnet for talent. It's precisely the kind of talent that industry needs to populate its programs. So it is the most applied university in the US and rated #1 public university in the US in the last 5 years. It's very diverse, about 30% of first-generation college students, 55% of student aid. It really reflects the diversity of the community in Los Angeles, the greater California, and the country. Its depth is unparalleled. It's one of the leading space science programs, flying instruments on every major NASA mission since the beginning of space age. And these are the magnetometer instruments that you'll hear about momentarily, some more, but also new instruments that we're developing now. It has huge breadth in space plasma physics in particular, heliophysics that I mentioned earlier, practiced across many departments. Being in the Southern California, it is at the heart of the US aerospace industry, and is highly committed behind making this work. I mentioned magnetometers. UCLA has been flying magnetometers since before the Apollo era, basically. And this is one example of them. Galileo satellite launched in 1989, went to Jupiter with a probe and an orbiter, made huge discoveries, including discovering that Europa, the moon of Jupiter, has actually an ocean that could potentially harbor life. And therefore, it's also participating in the future mission, the Europa Clipper, with a magnetometer that is going to launch in 2024. But recently, we have had a foray into launching our own satellites. This is one of them. It's a CubeSat that's inside the thermal back chamber, which you will get to see later on today. Inside, it's specially made copper box. And it's put inside the chamber now by one of our students, and then this is the chamber itself. You can see that. This is Alpine in orbit. It launched in 2018. There are actually two of them. These are pictures of them, flight models, and an engineering model, which you'll get to see downstairs. We use it for checking out our commands and operations before we actually upload to the satellite. Students do that. More than 250 students have been educated to the program since 2009. So for 10 years before launch, we have been working on this. And you can see teams of students, probably 3 or 4 generations of students went through, including the ones that are operating the satellite now. So very diverse group of students that are now in industry and doing great things over there. There are precedents for doing this. Other universities have centers like the institute we're envisioning. This is LASP at Colorado. This is the Space Science Center at UNH, and so on. But UCLA has such a breadth in terms of scientific activities and such a history that I think if properly structured, it can do a lot more than those other institutes. The website for the institute has been launched. There has been a kind of a study for potential business plan and strategy. Community workshop was done to solicit feedback and advertise the launch of the institute. An executive director ad has been out for a while. Interviews have been conducted and a hire is imminent. July 1st is set as the launch timeline for the institute. I think this will just mean the executive director has been hired and the master's program has been announced. And maybe that will be to start maybe in fall of 2023. There's enough time to plan for that. But beyond that, I think you will see a lot more activities in the program in terms of winning proposals for it and seed funding for activities in the institute over the next year. And the plan of how the funding is going to come through and what is it supposed to be doing. Inputs are the dollars. Activities are here in oval shaped objects, and so we have the research part of it, the entrepreneurship part of it, which is the Anderson School of Management. The education part of it, we all do education outreach. And funding is supposed to come out of extramural funding from proposals to NASA, NSF, DOD, and so on, to the tune of tens of millions. So we hope in the next few years per year. And support from the Vice Chancellor and for investors come in to fund ideas for new, say, startups. So support for can also come from the master's program. It's supposed to be self-funded master's program, so tuition. And in terms of what we produce, it's highly talented students, visibility of scientific exploration, and startups and industries, collaboration with industry as well, in terms of pushing the envelope with new technologies. That's all I had to say. Here's the mission and vision statement again, but maybe I can see if there are any questions at this point. And I'll be glad to show you the facilities downstairs that we had to put together the satellites. There are flyers back there that you can take on your way out if you wish that portray the institute in a nutshell. Feel free to them. And I want to thank Jacob Bordnick, who has really been spearheading this, Professor Bordnick from the Atmospheric Oceanic Sciences, leading the institute through its creation. I see a question. Yes.
Oh, you said you're starting your master's degree students. You also said on your chart you're going to do PhDs. So when do you think you'll be starting PhD student activities?
This already exists. They are typically funded from extramural funding from NASA programs, NSF programs, and so on. The master's is more like the professional master program, which we haven't had before. And the idea is if somebody is in the industry and would like to get extra, education in some aspects of space science engineering, and will tune it to the needs of the student, then they come in and spend a year or two taking courses, participating in some hands-on program, and then going off to industry to utilize that experience. Yeah.
Yeah, briefly, it said in the education, you wanted to promote diversity and promote it to acquire undergraduate students. How, I know you said you're in the early stages, but how do you plan on reaching those students?
The way I envision it anyway is that those students will come to the institute just organically by participating in ongoing research activities. And so like we did on Elfin, what we do is we just advertise. Word of mouth works the best. And we advertise that there's societies and functions that students have, and attract usually junior, I'm sorry, not junior, but frosh students and sophomores, because they have another 2-3 years to go, and our retention rate is very high. 90% of them stay all the way through graduation. So undergraduates start early and then get your feet wet, and they stay with our program. And so we get them like that. We typically, on a program like Elfin, we had about 45 students every year ongoing. In the summers, when they would like to go for internships, we let them go for internships outside. The experience they gain in internships in industry, they bring back. And so we like that. But they retain their connection with the group and advise newer students that come in on how to work through the summer. And so we have a number of students also in the summer, and the ones that get internships come back. So we have very strong ties with people as they during their advancement. That's the recipe. Word of mouth, work catered to their needs, and very tight involvement of staff and faculty in the day-to-day operations. That shows you care, and they care too.
What would be the duration of such a program for the students? Do they have to spend more time in college for that? Or
for the master's program, yeah, they would have to spend either extra year, for example, 4+1, or they have to spend 2 years. But that would be tuned to their needs if they come from industry to be like evening courses. So they could do that. In terms of participating in these activities, research activities as undergraduates, there's no extra time, just evenings, weekends. What else do they have to do, right? Very sensitive. They have classes to take, exams, and other priorities. But sooner or later, I think they click, and so their heart is really. They're very devoted to the program and to its success. Of course, a project like Elfin took 10 years. So, they graduate and then another crew comes in and so on. And the saddest time is when you see, a project manager or Elfin that has to go on to industry and they cannot stay for lunch, but we tell them, tears start coming out. But we tell them, no, you're still part of the team, you still participate, and we'll be always connected and so on. But but still, it took 10 years for the first one. It won't take 10 years for the next one. I think the next one will be 3 or 4 years. And so it's more, close to a student's career then.
Okay, thank you, Vasilis.
I see we're in time.
So you'll hear more about this. Keep your ear to the ground. Yeah. I guess it launches in 2 weeks, so.
Yes. There will be a public
Writing a
announcement.
date on the screen, right?
Probably a press release.
Yes, so what's the schedule now?
So this is right time, just Q&A. Or
Q&A.
break. Q&A or break.
Any more general Q&A, or do we want to take a tour downstairs, or are we gonna lose everybody? What did we think?
3:30, we start the aerospace.
Okay, so
Perfect time.
perfect time. We all need a break anyhow, get up and move around. So it's on the second floor?
Second floor, I'll leave you there. And we'll just start from Mission Operations Center and see where we operate the 2 satellites.
Right. Basically, we're going 1 floor below where we are now and a little bit that way. But just go down the stairway and then that direction. Down from 3 to 2.
Please make sure you come back at 3:30.
Come back, yes, make sure you come back. You can leave things there if you want, if you have bags or whatever. The room's not gonna be empty, right? You're gonna be here, Ken? You're
Yeah, I'll be here, yeah. We can actually arrange another tour for that facility if you like.
Are we presenting the?
It's Vasilis's thing, so I don't, it's not my,
Just me?
it's up to him.
So all the-
This is an
These are
anthology.
those 2 slides of
Thanks, Tom.
Hi, everyone. Thank you for the introduction. I'm Roxana, and today we're going to be talking about a JPL mission called Psyche, which is set to explore a metal asteroid, hopefully launching this year, but in a few years from now. So to start, we're going to ask you all some questions. So how far below the surface is Earth's core? Does anyone have an estimate of that or know the number?
7,000 miles, maybe? 6,000? No, 3,000 or 4,000.
Well, yeah, okay, a little bit off. Anyone else? Okay, well.
The center or the outside of the core?
The real expert thinks so.
Yeah, so the answer is, that's a good question. Do you know if it's the center or the outside of the core?
This is the outer part.
Okay, so the outer core is 1,800 miles deep from the surface. Next question for everyone. What is the deepest humans have dug into the Earth?
6 miles.
Sorry?
6 miles?
Yeah, close, yeah. Anyone else want to throw anything out there? Okay. Yeah, so 8 miles, so very close. So this was, as you can see, an over $100 million project that took 19 years. The drill couldn't go any farther past when it reached like 370 degrees Fahrenheit, which is nothing compared to the core temperature of about 9,000 degrees Fahrenheit and a pressure of about 3 million atmospheres. So yeah, so clearly humans have not been able to go to the Earth's core physically. So if we haven't been there, how do we know the composition of Earth's core? Does anyone know that? How do we? Yeah.
Magnetic field or something.
Yeah, seismic activity. So what we know about the Earth's core is from measuring the Earth's density. So in 1778, the Earth's interior was determined to most likely be metallic by Charles Hutton. As you all said, seismic activity measurements have been instrumental in helping us determine what is the fabric of the core. And then meteorites, as has been mentioned today. So many meteorites, as you all now know or knew previously, are believed to be pieces of cores of other extraterrestrial bodies, like other planets. So now that we've gone through these questions, that all takes us to the goal of the mission, Psyche. So Psyche is the largest of what are known as M-type asteroids within the main asteroid belt. So M-type asteroids are comprised of nickel, iron, metal, which are believed to be remnants of cores of larger bodies, such as planets. So Psyche was first discovered in 1852 by an Italian astronomer whose name I probably cannot pronounce well, in Naples, and it was thought to have been formed through hit and run impacts that stripped away a rocky exterior, leaving behind this metallic core. And what we know of Psyche's composition currently, prior to this upcoming mission, and its shape and size, has been we know that from various wavelength observations, including optical. And so that's how we've been able to build up our knowledge of Psyche prior to this upcoming NASA mission. And so knowing all of this, Psyche is of great interest to us because it can help us understand our own Earth's core.
And to give a sense of scale of that size, the average diameter of Psyche is about the distance from here to San Diego. So it's quite large.
Yeah. And so here's a video that NASA created as a trailer for the mission and kind of gives an overview of the goals of the mission and the folks who are involved in this project at JPL as well as at ASU. So this video gets me really excited about the mission, so I hope it has the same impact on all of you.
There aren't many classes of objects left in our solar system that we haven't looked at up close with a spacecraft. And one of them that's left is the metal asteroids.
16 Psyche is an asteroid that orbits the sun out between Mars and Jupiter.
The reason that Psyche is unique is that it is metal rich.
It's believed that it may be a remnant core of an early planetesimal that was formed in the very, very earliest parts of the formation of the solar system.
And after this planet started forming and this metal core formed inside of that, it collided with other bodies that then stripped off the rocky mantle, leaving this core in place.
This is the part of planets that we can't sample directly today.
It's too hot, the pressure's too high, our instruments would melt. Can't drill a hole that deep in the Earth or other planets. So how do we study the core of our planet?
Psyche gives us the opportunity to visit a core, the only way that humankind can ever do. And it would be the first metal object that humankind has ever visited.
We've been approved to go in August of 2022. It'll take a number of years to get there.
Flies past Mars, gives us a gravity assist, uses our propulsion system to then slowly creep up toward the end of 2025, getting there in early 2026.
We'll go into 4 concentrically smaller orbits to collect the necessary measurements that we need from our 3 primary instruments.
So our payload consists of a couple of imagers, which are cameras that take pictures of Psyche. Also a gamma-ray neutron spectrometer, which allows us to measure the elemental composition of the surface of Psyche. And then a magnetometer, which will allow us to detect any magnetic field that's left at Psyche.
If Psyche still has some sort of remnant magnetic field, that probably tells us it really was a core. It's a strong indicator. We also use the radio on the spacecraft as an instrument, so we can map out the gravity and map out the interior structure that way.
We're using a particular thruster technology, Hall effect thruster technology. They operate 5 times more efficiently than normal rockets, so they use a lot less fuel, and is what allows us to get into orbit around this asteroid.
Solar electric propulsion has been around for quite a while, and it has flown before, but we're continuing to push the boundaries. We're going to have big 5-panel fold-out solar panels that will provide the electricity for the thrusters, which use as propellant the noble gas xenon.
This will be the first time that Hall effect thrusters have flown in deep space.
Studying the evolution of a planetary body is a detective story.
There's a magic to when you actually are on the launch pad and you say, we're go for launch.
And you feel like singing and dancing and you feel like throwing up at the same time.
Let's go discover things about our solar system that we have no other way to do. I think that it's fundamental to who we are and also who we should be. It's an incredible opportunity to be a part of the team making that happen.
Okay, so a lot of this we just saw in the video, but this is a NASA Discovery mission, and the PI for this project is Dr. Lindy Elkins-Tanton over at ASU, with some collaborators also at ASU and at MIT. And then the project itself is managed by NASA JPL, and they're also working with Maxar to build the solar electric propulsion chassis. And so the main objectives for this mission are, as we mentioned, to determine whether Psyche is a core, or if it's rather a primordial unmelted material, determine the relative ages of the surface of the asteroid, and then also determine whether small metal bodies incorporate the same light elements into the metal phase as are expected in our Earth's high pressure core. Determine whether Psyche was formed under conditions more oxidizing or more reducing than Earth's core, and then of course to characterize Psyche's topography. And so we have a very large team across all of these institutions that we mentioned working towards building the spacecraft to achieve these goals. And so, as also mentioned and shown in the video, there are a number of payloads on Psyche, including a multispectral imager, a magnetometer, the gamma ray and neutron spectrometer, which are shown here, the gravity and radio science investigation, as was mentioned, as well as they're doing a demo of deep space optical communications, which I believe this is the first mission that is being done. So that is also very exciting. And then, of course, this is the first mission to a metal body rather than rock or ice, which is all of the prior missions. And currently launch is scheduled for this September from Cape Canaveral aboard a SpaceX Falcon Heavy rocket. So the spacecraft is actually down in Cape Canaveral right now. And yeah, teams are very busy working to make that deadline happen.
I'm Ben. I'll take it from here. So this here we're looking at is the trajectory and timeline of the Psyche mission in a snapshot. As Roxy said, launch is scheduled for September of this year. And the first 70 days after launch is a critical period. The first days after launch is critical for any spacecraft launch, where here we're deploying the solar arrays and doing initial vehicle checkouts to make sure that all the systems are healthy as we start the trajectory. And this overall trajectory you can see is a very characteristic sort of spiral out trajectory. It's characteristic of the solar electric propulsion, as Roxy mentioned. So we'll be doing the solar electric thrusting out to a Mars gravity assist in next May, and then continue the solar electric thrusting out to a Psyche capture in January of 2026. Yep.
So is this the first interplanetary launch for the Falcon Heavy?
Didn't the Heavy demo, wasn't it supposed to do a Mars?
I know there's a Tesla on the way to Mars, right?
Yeah, exactly. But in terms of non-demo missions, I'm actually not sure.
I'm not sure either. That's
Yeah.
what it is. Yeah, interesting.
Yeah. Yeah, and then so after Psyche capture in January 2026, there'll be a little over a year and a half of orbital ops at Psyche doing the science data gathering until nominally October of 2027. And so again, the Falcon Heavy launch plus the Mars gravity assist plus the solar electric propulsion has us arriving at Psyche in about 3.5 years. So this is what the Psyche mission overview at the orbital ops at Psyche looks like. If we start out in this higher orbit with the magnetic field measurements with the magnetometers and the imaging and mapping with the imagers. And then after 56 days, drop down into, or spiral down into orbit B, which is same inclination, but just a lower orbit, continuing with sort of topography and geologic mapping with those imagers and continuing with the magnetic measurements. That's for another 80 days, and then to orbit C, spiraling down to there, again, lower orbit, but slightly inclined to the other two. where here we start with the gravity science investigation with the X-band high gain antenna, and continue with topography measurements. And then finally the orbit D, which is highly inclined to the first three, and even lower. And that's where we start to do the composition measurements with the spectrometers.
Question, no intent to any touch the asteroid kind of operation?
No, there's no sample collection or contact. Yeah. Exactly. So this is what the Psyche spacecraft looks like. You can see there's the very photogenic cruciform solar arrays there. And then, some of the science payloads. So you can see the deep space optical communications technology demo is kind of off to the side. It's basically laser communications at high rate, and it can position itself independent of the spacecraft attitude, so it can actually undock and redock with the spacecraft. So it's kind of its own thing hanging out on the side here. And then you can see just kind of pointing out the others here. The imagers are off to the side. The magnetometers and spectrometers are off on booms, so you kind of avoid all of the interference from the avionics on board and radiation that could originate from high energy particles hitting the spacecraft and stuff. And then there's that high beam antenna on top for the radio and gravity science investigation. And here's just a nice photo of the Psyche spacecraft in ATLO in the assembly test and launch operations environment in JPL. And you can see it's got kind of a footprint of like a smart car basically, and it's as tall as a basketball hoop. So just give you an idea of the size of the vehicle. So we talked about a large cast of characters here, and we mentioned we're from Aerospace, but Aerospace hasn't come up. So we're going to talk about what we're working on. We, Roxy, myself, and our teammate Kim are embedded within the JPL team that is performing testing and data review of the guidance, navigation, and control subsystem. So that subsystem largely is responsible for determining where the vehicle is, figuring out how to go to where it wants to go, which is Psyche or the flyby, and controlling the vehicle to meet those goals. And so we are verifying and validating the GNC requirements and functionalities sort of at the higher system level of the broad satellite level, and ensuring that the sort of GNC behaviors and the hardware manager software performs as is intended. And the GNC hardware, there's a whole mess of different sensors and actuators that you need to actually control the vehicle and accomplish the mission, even independent of all of the science payloads. So what we're working with the inertial measurement unit, which measures the rates on the vehicle, the solar array drive assembly. So the solar arrays can actually point independent of the pointing of the spacecraft, or they can rotate independently to be able to see the sun independent of the antenna pointing or the science payload pointing, for example. Then we deal with the cold gas thrusters and the reaction wheel assemblies, which are in charge of pointing the whole spacecraft. Sun sensors and star trackers, which are used to determine where you are in space and how you're pointing relative to all of space. The solar electric propulsion gimbals, which can point those Hall thrusters relative to the spacecraft body. And then all of the associated avionics, which the electrical boxes that communicate with all of these things. And so our role is to, again, test to make sure that the Psyche spacecraft will know where it is and will be able to control itself to arrive at the Psyche asteroid eventually. And And I apologize to Ed Wong, who is here with us in the room. He's also an aerospace employee working on Psyche, but on the avionics side of the house. So sorry I didn't get inputs from you, but feel free to chime in if you want to talk about your role. So I guess we can. And yeah, so that's all the technical background that we had on the Psyche mission. But we're happy to answer any questions. But so Psyche is so named for the goddess of the soul, and I think just because of how important it is to understanding, our own planetary core or development of planetary cores in the solar system, and this sort of connection to the soul, I think it's gotten a lot of excitement among everyone, but that includes ASU students, and there's a lot of artwork that has come from the ASU student population, from anywhere from art students to engineering students, or across the entire university. So I thought it was cool to just share these two out of many pieces with you, and you feel free to include a link here. You can feel free to check out more at the website. So that's all we had. This is the JPL Psyche team. Unfortunately, Roxy and I didn't make it into this one, but yeah, thanks for hearing our talk. Hopefully, inspired you to follow the Psyche mission. Any questions?
So what does the 16 stand for?
And that
16th asteroid discovered.
Yeah.
How common are these metal asteroids?
I think they're fairly uncommon.
They're fairly uncommon, but I couldn't give you the exact percentage.
But I mean, it's like not more than like 10 then or something.
Oh, yeah, yeah, I'm sure. Yeah, I don't know how many asteroids we keep track of. I think it's 500,000 or something.
In the middle type.
Yeah.
Yeah, I have a couple of slides of this, so I'll show you a little later.
Yeah, but in terms of this size, well, Psyche, as I mentioned, is the largest of the metal asteroids. But yeah, I'm not sure what like the second largest, for example, would be.
Is there any residual capability afterwards to go visit anything else?
Well, I don't think. I think that there's if the spacecraft is still healthy at the end of these orbital labs, I think that anything else would be to continue studying Psyche. I'm not sure what the Xenon budget is to be able to thrust elsewhere in any nearby objects. So I think, if I remember correctly, that any remaining budget would just be studying Psyche further. And I think that there is a budget for like a disposal essentially as well to steer clear and not hopefully impact Psyche.
Impact it?
Yeah. Oh, sorry.
What level of residual magnetism are you looking at?
So we're not part of the science team. I'm not sure. I think. Sorry.
I would expect thousands of nanotesla, but still that's 10 times smaller than the Earth's field on the surface.
Mm-hmm. Yeah, I think that if they, I'm not sure what the bounds are, but I think any above a certain very low threshold maybe would be huge in demonstrating that potentially Psyche was actually a core.
Yeah, prior flybys, IDA, Gaspra, and other asteroids have given fields on the order of 1,000 nanotesla at the surface. But this one being bigger, it may be larger magnitude. So if you type maybe 10,000, it's 1/5 of the Earth's field at the surface.
Okay.
When you get there, what percentage of fuel will you have left in your cold gas thrusters?
I don't know the exact number.
I don't know if this happened.
Yeah, there.
Sorry, yeah, I don't even know what to guess. Yeah, a lot of because it is a 3.5-year journey out to Psyche, and the analysis timeline for Psyche is fairly compressed, especially from a GNC perspective for this mission. A lot of our work is focusing on checking out the capability that's going to be used in the initial post-launch checkout phase, and making sure that the vehicle is safe and can point to the sun and be power positive, all that kind of stuff. And so I don't think I haven't looked at anything personally that is out at Psyche.
Depends on your insertion error also.
And when if we don't launch in September and we have a different trajectory, then different flybys that could impact the residuals.
Any particular GNC challenges on this project versus other projects that you've been involved with? Anything that required special thing to learn, to acquire, to do, complicated, or is it just a standard thing?
Well, so this is my first real spacecraft program that I've worked on.
This is my first one as well, I was gonna say.
Yeah, most of my experience is on launch vehicles, which is a very different beast in terms of this types of activity. GNC is one of the areas that is hard at work trying to meet our current launch date. And part of that is because I think because of the unique relationship with this mission, where the bus is being acquired from Maxar as sort of an off-the-shelf product that has had to be modified slightly for deep space usage. Some of the GNC capabilities came later in the development cycle than in other, JPL missions of this class, for example. So, I mean, it seems like maybe a learning point there is just make sure you leave yourself enough time to do the work that you need to do, and manage that. But otherwise it's largely been a learning experience for me in terms of how this sort of spacecraft GNC verification and validation work goes.
Do you plan to publish the GNC part of thing on like AIAA journal? AIAA has a GNC journal.
Okay. I'm not sure.
I think that would be up to the overall team at JPL, but yeah, I don't know if that's currently in the works or not.
Yeah, other parts of the project have been published.
Yeah.
Or are in the process of being written up to publish. But
I think the AIAA GNC journal is a very significant part of the publication for many years.
Okay.
Just consider it's a good source of publication.
Yeah, it's good to know. Yeah.
Yeah.
I'm sorry, was somebody else?
I don't know who's first.
I may have missed this, but who manufactured and where was it built? And what is Aerospace Corporation's involvement with this?
So the majority of the what we call the bus, which is sort of the core of the spacecraft with the solar arrays and things, that was manufactured by Maxar, who are located up in the Bay Area.
Formerly Space Systems L'Oreal.
Yeah,
yeah,
exactly. And they, took that product, passed it off to JPL, who, did their own sort of assembly operations, incorporated science payloads, and that kind of stuff. So
assembled what you see here.
Right. Yeah.
So that's at JPL.
So that's, is that in the Bay Area?
No, so this is in Pasadena and that's the JPL.
Yeah. But a lot of what you see here was handed off by Maxar to JPL. And then as for Aerospace's role, so Aerospace typically we do a lot of work on the defense side of the house with Space Force, National Reconnaissance Office, that kind of thing. But But aerospace has been kind of branching out into more civil work. You know, we worked with Ahum on the Artemis program, and there's been more and more involvement by aerospace in JPL programs, and JPL has been requesting aerospace support on a lot of their programs because we have a lot of the same experience base. Go figure. And so on Psyche, it's been more of a team by team basis as to what aerospace's involvement is. So they've reached out to our program office and said that we need help with this thing, and that they reach out to the aerospace team who's responsible for that sort of area of expertise, and they get help for that team, and that it's kind of piecemeal and happens independently.
Maxar is a company, if you look at news, they took a lot of Ukraine satellite images over Ukraine these days.
Oh.
A lot of the Russian tanks movement, they were taken by Maxar.
Oh, interesting. You still have a question?
I was just wondering, you said this was a modification of a existing design. Did the original design have an ion engine on it?
Yes. Yeah. So this is
one?
Maxar's. This is Maxar's the solar electric propulsion chassis. But this bus design with that thruster has not flown in deep space. So it's all been sort of Earth orbits, Earth operations. So that's where a lot of the modifications had to come in, was modifying for deep space use.
Does this have by using the ion thruster, does that give you a lot more space for the gas for the they cold gas thrusters and all this sort of stuff?
Oh,
it does? Or?
Yeah, I mean, I guess that probably it informs the form factor, dictates the form factor of all of the components that you can fit within. And I forget, I mean, there's, yeah, I think there's a very substantial tank for the cold gas thrusters inside the core of the vehicle. And it does allow it because you use ion thrusters.
And we have a question on that. Holger, go ahead. You can unmute yourself. Holger. Mr. Eisenberg.
Oh yeah, so thanks for unmuting. Yeah, I wonder about if the spacecraft has some way to measure the electric charge of the metal asteroid, if it has some, because I've heard that the spacecrafts are charged up in space up to 10 kilovolts in extreme cases, and maybe also this metal asteroid.
It's a good question. I guess looking at.
Holger is is in Bay Area. He's an engineer in Bay Area.
Oh, cool. Yeah, I'm not sure about that. Again, we're not on the science team, so I don't know if. I mean, you see this is the list of the science payloads. So I'm not sure if any of these could be used to measure that. Yeah.
I can address that.
So indirectly with the magnetometer, of course, if you have some moving charge, but the electrostatic charge would be interesting.
Yeah, it's difficult to do that because Psyche is embedded in the plasma, and the plasma neutralizes any charge to a distance of a few centimeters. So unless you are within a few centimeters from the surface, which would be very unfortunate, you could not measure the charge.
Yeah, stay outside the discharge length. Yeah.
Yeah.
That's good to know. Thank you.
Okay. Yeah.
How risky is this project? And are there any big uncertainties for it to fail or not fail?
Well, I think it's more of a time crunch sort of thing. Like we have the September launch date, which previously was an August launch date. So I think it's more of a matter of making sure that we're at the level that we need to be, like with the testing that we're doing, like for the GNC system, for example, by September, and then, you know, analyzing that. And if we're not there, then, you know.
Once it's up in the space, are there any, is this mission going to be doing anything that hasn't been done before?
Exploring a metal asteroid. The only the using the Hall thrusters in deep space is new, but I'm not sure how risky it is necessarily. The DSOC, the Deep Space Optical Communications, that's a new technology, but it's only being used in a sort of tech demo capacity, where, you know, we have multiple other antennas for communications. It would just be a nice to have the high rate of communication.
I think this mission also has a lot of unique payloads in the sense that since it is a metal asteroid, like the sorts of sensors that wouldn't normally be on this sort of mission. So I think just like having all of these various payloads together is, I guess, new in a sense.
Has this bus flown in deep space before?
No, not this particular one. Yeah.
Actually, off that, you said that modifying the bus to fly in deep space was one of the big challenges here. What exactly is that challenge? Or what do you have to do differently there?
Might be radiation could be one factor.
Yeah, I think using radiation hardened electronics was part of it. There might have been also like additional redundancy built in.
Yeah.
But I can't speak to the specifics off the top of my head, unfortunately.
How many reaction wheels does the spacecraft have?
4. Yeah. So it's single fault tolerant, redundant in terms of reaction wheels.
Yeah.
I wonder if I can't remember off the top of my head if the solar panels for Psyche are the same as the SCP chassis from Maxar. I would imagine that we need to have more power for the SCP operations further away from the sun. You know, where Psyche's average like orbital radius is about 3 times as far away from the sun as from the Earth. So there's a lot less power being generated per square foot or whatever, as we would have it Earth.
So you're using, you said Hall thrusters, right?
Yes.
So are you firing, Hall thrusters produce a torque, are you firing them in pairs?
Well, so that's produce a torque. So the Hall thrusters can be gimbaled. The ones that we have can be gimbaled, and so I think for like steady state operations, the idea is to point the thrust through the CG as best as possible to try to reduce the torques. But then, there are strategies to use the reaction wheels to counter it. Also use the thrusters to unload.
Thank you. I think in the benefit of time, we can move forward with our STEM program. Thank you very much. This is very exciting. I don't know if it is just any bearing on planetary defense, but it's a purely scientific mission, but it is super interesting project to be involved with. So thank you very much.
Of course, thanks for letting us know.
And I think I'll connect my laptop now because this will be in there. So give me a moment here to.
Okay.
which was.
The 20.
For those who came late, we have the badge on the back, on the table. If you haven't got your badge, welcome to get it. Everything good?
Go back.
No. It's not connected.
Sorry.
If you need it.
I can just do here.
I don't know if you
Right now.
want people to pass USB. Your company computer.
Yes. What is it?
If you want
Okay, we're good?
if you want a pointer, I suggest the stick is the pointer.
Oh, no, that's fine. Oh, just to advance.
You have to plug in
Yeah, that's
USB.
better. That's hard to see on the screen.
Yeah,
The
that's fine. I'll just.
laser pointer is hard to.
If you share the slide, we need to share the slide on Zoom.
Oh, now whom are you on Zoom?
Can you share the slide on Zoom? Did you log in on Zoom? You have to share just like you are home. Share. Zoom. Yeah. Share.
Okay, I can.
The green one, the button, the green one. Yeah. The 2022.
Bottom right now. Okay.
Okay.
No.
Okay, you all set.
Give us that.
Thank you. Oh, it's okay, thank you. I'll just do it from here. That's okay. All right, good afternoon, everyone. My name is Monica Maynard. I am STEM Outreach Coordinator for the Aerospace Corporation. We're a really small team under the Corporate Social Responsibility team within corporate communications at the company. So mainly what we do is we do STEM outreach with K-12, first generation type of students. We reach out to schools and we employ the expertise of engineers and scientists to create cool lessons that then we can share with teachers and bring them to schools. We also have a database of volunteers who help us out at like science fairs and Ask the Scientist nights and community events and things like that all over Southern California. This presentation is based on the work that we've done with Dr. Nahum Melamed, and he will be speaking to a couple of the slides because he put them together. And I mean, he's the engineer who created the app, so he'll be able to tell you more about that. But here's just a little bit about the company and what we do with corporate social responsibility. So I'm just gonna play a video real quick.
The Aerospace games.
Yes, coming up, so sign up.
So I've got my essay written, and I've been working on it for about a week. So now I'm gonna show you how I use Grammarly to edit. Okay, so here's my essay.
Okay, no.
At Aerospace, our people are our most important resource. Whether it's introducing our K-12 learners to the exciting world of STEM, providing mentorship and career opportunities for talented college students, or giving back in our communities, Aerospace cares. Our social responsibility program supports our commitment to create a workforce that leverages diverse perspectives and experiences to deliver innovative solutions for the nation's space programs. Our goal, to inspire the next generation.
Okay, I lost where I was. Can you help me, please? Looks different than my computer.
What's the PowerPoint?
Just
Just a P, okay. An optical. Very good. Thank you. Sorry. So I am not the tech person, obviously. All right, so basically what we do is we try to inspire, the next generation. A few years ago, we started the STEM Endowment Scholarship, which picks one student from Title I school and basically puts them through college. So that these one student out of 9 school competes to get the scholarship, and it basically awards them a $10,000 scholarship, renewable for the next 4 years, with the opportunity to also work at Aerospace as an intern. So just this year, one of the students from one of the high schools where I work got chosen, and he will be coming here to UCLA. The first student who got the scholarship also came to UCLA, and she majored in math and will be becoming a teacher pretty soon. So no one can predict where the future of space innovation will lead us, but we can certainly help inspire these students. Currently, we do classroom visits. Since the pandemic, we've gone virtual, like everyone else did, and we accommodated a lot of different programs. We run a teacher program now open to national teachers across all our offices. We also have a STEM Institute for high school kids from grades 9th through 11th grade. And then just last year, we started the Aerospace Academy, which is designed for students in 12th grade and going into college from the Title I at-risk background. And we basically just kind of mentor them and show them all the cool things that they can do with the STEM career. So definitely all the help that we get from our volunteers is really vital to the work that we do. We also partner with other nonprofits and community organizations throughout LA that work with these at-risk communities, and we bring them over when we're able. We bring them over in person and give them tours of our labs. We have 6 physical science labs, and the students get to see all the cool equipment like we saw here, and they get to hear from the scientists and the engineers who work in those fields. So that's just a little bit about what we do. Dr. Nahum Melamed worked with Paul Chodas and his team, and they developed an app that is physics-based that is now available to the public. So we kind of, when Nahum brought it to us, I mean, I took his class like twice already at Aerospace. I still have a lot to learn. And what I was thinking is we can actually do this with some high school kids. Let's figure out how to do it. So we actually, before it was even like completely public, right? We got some computers, we had some kids on campus for the Institute back in like 2018, and Nahum ran a couple of scenarios with them. So that was kind of like the first time we used this as an educational resource. And then since then, we've been able to create a unit, a lesson plan that teachers can now just print out, have the slides, and be able to teach it. And then we do offer these spectacular audience with Aerospace about once a month. And about once a quarter, we invite Dr. Melamed to come and do one of these talks where he talks about, the purpose and the reason behind creating something like this. And then we engage the kids in a demo, and then then he turned it into a competition, which is, something that I always do in the classroom. So if you'd like to continue the next couple of slides.
Okay, thank you. So we had the fortune to collaborate with JPL on this project, which is intended for their mission designed to deflect an asteroid with the use of a kinetic spacecraft. The spacecraft that's going to collide with the asteroid and deliver its momentum to the asteroid, nudge it a little bit, of course, enough hopefully miss the Earth, and that's what you see here. So the original impact point is somewhere within this red circle here, and mission success is moving the dome outside of the red circle. We have orbital mechanics embedded in behind the tool. We have launch vehicle performance embedded behind the tool in the engine of the tool, and it is approximated to make it interactive. So as you move knobs, things move, and you can actually play it in almost real time. It gained a lot of respect with the community because it can be used to find ballpark solutions very quickly. You don't need to run simulations overnight with heavy computers. You just guess a few things and things move in front of you on the screen, and you can then take those initial guesses and feed them into the high fidelity simulations, get the actual mission design solutions for this particular scenario. I'm going to give a quick demo during my portion. But basically, there are several panels here. The upper panel is the mission design panel. It has several parameters that you can change, several knobs and parameters. Here you see the distance between the asteroid and the Earth. It comes close and far until it hits the Earth right at this point is 0. We have 30 years of simulated data. Everything here is completely simulated. And time 0 is right there, this red dot. Here are the orbits of the asteroid, the orbit of the Earth around the Sun, and the orbit of a deflector, if a solution does exist via a Lambert solver. So there is a Lambert solver in that engine which calculates the transfer trajectory, and these are the outcome numbers here in terms of the change in velocity, the relative speed between the spacecraft and the asteroid, and so on and so forth. And again, the goal here is to move the dot that by design is going to be sitting inside the red circle, the red capture circle, move it outside by some comfortable amount. The reason why the red circle is larger than the physical Earth is that because when the asteroid approaches the Earth in the very last minute, it gets pulled in. It's called gravitational focusing. And so we need to compensate for that by moving it slightly outside of the physical Earth to make it actually miss the Earth in the last minute. So recently, so this tool is available both on the JPL website and on the Aerospace website. But recently, as a result of our experience with mostly high school students, we decided to create competitions in which the students compete with one another to deflect asteroids. So the Aerospace version has a teaming option there that you can turn on and conduct asteroid deflection competitions with the tool. We've done it at Aerospace, where we involved our own SMEs and they created very challenging scenarios, and they had to really work hard to win the competition. You can do it anywhere. With high school students that are hitting this score, we give them simplified scenarios, but they have fun, and we have done it several times over before COVID, during COVID, and now we're looking into in person after COVID. So if anybody wants to participate in an asteroid deflection competition, or know a local high school that would like to do that, reach out to Monica, and we can organize one of those workshops where the students will compete to deflect an asteroid. So do we have one more slide? So yeah, so I think this is pretty much the same thing.
Yeah,
Oh,
just
so
going
this is
over how.
This is the teaming version. We just turn this on, and you can choose a team name, and you can set up the campaign parameters, right? How many launch vehicles are there to you? When was the asteroid discovered? What is your budget? You can actually design a kind of semi-realistic mission to the asteroid and try to win by creating a performance metric that is of the highest value. The highest value of the performance metric is the winner. And the student, it creates a dynamic in the room. You know, everybody wants to win the game. And it is one of those things that creates interest.
And it's definitely, you know, better to run it in person. So we have the computers, we have them in teams, and you can hear what they're saying and they're listening to other teams, and we're putting numbers on the board. So it's really interactive. We tried it on Zoom last year. It still worked in the breakout rooms, but they weren't able to hear all the other teams and, you know, kind of peek in and see that. And you get a lot more kids that don't turn on their cameras. So that was a challenge, but that was a challenge that every teacher in the nation was having anyway. So we were trying to also brainstorm, how can we do this better so that, you know, the teachers can use it in the classroom. So, so hopefully once we come back in person again, we're able to run these and just have a competition. And just like a little bit of background, the time that we ran it with our high school kids before the teaming capability and and putting it on our website came up, we had to do a lot of background. So we couldn't just give the kids this and then just do a quick demo and then here you go, just do it. We had to go back and whom did a talk about, you know, the different types of asteroids, where they're found. So we did have to do a lot of that background. And with my background in geology, we're able to kind of bring them up to speed because that's not something that they normally teach in high school. I mean, it's part of the standards now, but a lot of districts are kind of behind on that. And so they kind of stick to the regular, you know, the biology, the physics, the chemistry, and they kind of push the earth science, geology, especially the astronomy to the side. So we kind of had to bring them up. These kids that come to us are highly motivated. We don't take, you know, we don't have a GPA component that we look at. The kids just have to apply to come to our programs. But they're self-motivated. So even the 2.0 students are right up there with the 4.0 students, the 4.5s, asking the questions and getting involved. So it's really a good program. Your kids came through this also, right?
Yes, they did. And in fact, I might mention that my whole involvement with that type of STEM activity started with my wife who sits in the back and my son who sits there. When he was in elementary school, my wife said, can you come to the school and talk about what you do? And this is one of the things that I can talk about what they do. So that inspired me to develop a few slides to talk about this. And after 19 years or 18 years, it evolved into what we are doing now, which you never know where you start and how far you go. It's completely random. Yeah, thank you.
Yeah, and I digressed a little bit. I didn't properly introduce myself. I've been working for the Aerospace Corporation as a STEM outreach coordinator since 2012, part-time, mainly in the summers. My full-time job is being a teacher, and I taught geology or science, AP environmental science. I currently serve as a teacher on special assignment for an LA district, and so I oversee all science. So I get to see more or less where all the gaps are, and so we're trying to plug in because the districts here in LA County and really almost everywhere, they have similar problems. So, you know, what doesn't work in my district doesn't work in LAUSD, doesn't work in ABC district, doesn't work in Norwalk La Mirada. So we're trying to find where all these gaps are and trying to plug them in as the Aerospace Corporation STEM outreach program. And so this is us when we ran it in person, and this is Dr. Malamed, and also when we ran it on Zoom. You can see that only us and had our cameras on, like the team, and that was run with teachers. So we do provide teacher support, and they're able to connect with us after the workshop and be in contact with us. We do go out and do school visits. So, you know, we tried using this app, you know, we try to help the participants to go beyond, you know, think beyond what they have to teach. There are other things, and there are other ways that they can teach more complex science and engineering. And then just engage different perspectives, especially with the students. They come from their world's really small when they're in high school. And, you know, bringing them to a company and seeing people, you know, how they dress, how they act, how they talk at work, that's really powerful. So that's one thing that we were missing from the online. So I'm really glad that we're slowly coming back. But yeah, it's super helpful. We also force them to communicate, you know, potential solutions. So we actually had like a little presentation they had to do when we were in person with their team and talk about some of the challenges that they had. That we don't give our kids enough practice in school to have that oral discourse. So we're, you know, trying to, again, fill in the gaps with our STEM program. And we presented this to teachers and students. I changed the number, but I didn't change the word. Nahum ran it in May. You did another audience with aerospace. So we are actually up to 10 workshops now using this NEO app since 2018. Again, the first one was with our students and our teachers. And when we survey our participants, about 90% say it was excellent. The other 10%, they didn't submit anything. So, so I technically call that 100%, but anyway. But 100% said they would, participate again. And we are, in our plans is to continue to do STEM outreach events. We actually have expanded our lessons. Aside from Dr. Malamed's NDA app, we also have a tardigrade lesson that's ready to go for teachers. We just launched a CubeSat unit, which will run for about 2 weeks in the classroom, which includes how to write a proposal to NASA or NSF or whatever, like how you would do that and go through the process. And then there's like a cute activity where you can actually build, with paper and cardboard, your own CubeSat and put little gadgets on it.
The tardigrades and the CubeSats related? Do you put the tardigrades in the CubeSat?
No, no. The tardigrade lesson is one of our scientists grows them in her lab, and that is not really like what she does, but she just finds them very interesting.
Because there are experiments like that.
Right.
And we launched the tardigrades.
Yes.
Somewhere else.
Yeah, to the moon, and then we looked it up. So she brings that up in her talk, that they were sent to the moon and they lived for a while, and that scientists were trying to figure out if they were still alive, and it turns out that they weren't, and so then the kids were all sad. Yeah, they're like, oh no, we believed in you. But we talk about the, NGSS is really three-dimensional. So we're trying to integrate all the other sciences and to show that they're all integrated, they're connected in some way. And so we try to do this whole systems thinking approach when we do our lessons. Yeah, and so then we also presented this last year, and then at the Planetary Defense Conference, and then we're open to partnering with other organizations who do outreach like us that would like to do stuff with us as well. And I believe that's.
So if students would like to compete on this asteroid, we can organize them.
Yeah.
That's very interesting. Thank you.
Yes.
So if students like whatever demo or presentation or workshop, are there any ways that Aerospace continues relationships with certain students who demonstrate an interest and want to keep?
Oh yeah,
more?
We do actually. When we started the High School Institute back in so we had the teachers 2012, and then in 2013 it was still just teachers. 2014 we brought in the high school kids in person for 2 days, and we've been in contact with those kids. We survey them every so often. A lot of them have already graduated college, so we invite them to come and be part of our panels, talk about where they went, what they're doing. Some of them, two or three of them from the initial Summer Institute became interns, and they had no contact with Aerospace prior to coming to this, so to the program. So, we call that success. We need more of that. So we're still kind of figuring that out, but then COVID got in the way. We've been staying in contact with kids, but we definitely want more. But then you also have the kids that go to college and change their mind, and then they become doctors or do other things. So it's like, darn, we need you here too. Yeah.
And I might add to that one more thing is that we differentiate between K to 12 students, which is they're being introduced to it without knowing much, but I also give talks and this kind of publications to college students, to the AIAA in fact. And college students are becoming interested in that, they would approach me and say, oh, I would like to be associated with aerospace who does this type of cool activities. And this is the right time for them because they might be a year from graduation and say, yeah, can we get connected with somebody who can tell us what it, so, you know, it's, I would say that probably the age group that is most inspirable are the elementary school kids because they just jump out and want to know more and more and more and more and more. So they have like 10 or 15 years before they decide what to do with their life, right? So I might ignite something that will, you know, manifest in 10 or 20 years.
Yeah.
But those students in college that are ready to graduate and they say, oh, that's a project I'd like to be part of, they might contact Ben or Sarah or somebody else and say, can you connect with somebody who can, so this is different, it's kind of more related to the stage which the students are on.
Yeah, but we definitely, at least the populations that I work with, like I said, Title I, high risk, underrepresented minorities, you know, they don't have an engineer at their house. They don't have a scientist at their house. Their uncle doesn't work for aerospace, you know, so they don't see that. And so this is a good way to bring them on campus and actually show them what it's like, and also bring the teachers to let them know there are resources for them, because sometimes we're just so bogged down with everything that happens at the school, and the principal wants me to do this, and this kid's not coming to school, and I have to call this parent and do all these other things. And then our classes are like, you know, 34 students and higher. So you can't manage to also find your own resources. So us taking it to them also is really helpful. Yesterday, I was online. They had an in-person workshop in Albuquerque, our company did. So that team is amazing. They were able to get permission to do it in person. So I joined on Zoom. Those teachers were starved for resources. And I don't know if you know too much about New Mexico, but they don't really spend a lot of money on education. So for them, I mean, and all our programs are free. We don't charge anything. And, you know, they had, I think, like 13 teachers, and they're like, this is the best thing that's ever happened to me, you know, because we're not just feeding them, okay, you have to do this lesson and then you have to align it to this. We kind of just do the technical stuff. Yes, there is a stuff, but you're the expert. You run it how you want to. And so they said those were the best resources that they can get is, you know, we just want to know because we can't get out.
So who supports the teachers' participation? Is it their districts or does Aerospace?
Aerospace, our corporate social responsibility puts these on. We have a very small budget because we're also an FFRDC, so we don't have like, you know, millions of dollars like they feel us to put on an education department. So I'm the only teacher. We have somebody who is, she's a meteorologist. She's doing a lot of our social media. And then we have another person who focuses just on public outreach. And then we are led by our assistant director. So yeah, we're a really small team. We mainly rely on volunteers to come help us out. Occasionally we may have a couple hours for them to, you know, create something like the app, you know, to modify it for our populations. But yeah, it's all aerospace funded at the moment.
But like the teachers get a stipend or something to attend, or?
No, the teachers just get to
doing it
come for free.
okay.
So it's like a conference that they don't have to pay for. And we feed them lunch when we're in person. Yeah. And that, as a teacher, yeah, I'm there.
Is this considered as a continuing education for the teachers?
We do provide certificates and letters for them from the company saying that they spent so many hours, and the letter is to serve to, yeah. In California, teachers don't have to do extra hours, but like in New Mexico, Colorado, Arizona, they have to do a certain number of hours to keep up their credential, and they have to submit that. So when I get back home, I need to create those for the teachers who participated yesterday.
And if you want to learn more, here is the.
Yeah, actually, yeah, starting next on June 29th, we're launching our teacher workshops. We have 3 this summer. From 9 to 11 on June 29th, and then the next the next 2 weeks after that. So once a week for 3 weeks. And then our Summer Institute will be the last week of July. So we're prepping for that. So, signups are still available if you know of any teachers or high school kids who would like to participate, and you can access those just by going to Aerospace STEM events.
Okay, yeah. Thank you. Question from.
I just checked so everyone knows the Aerospace games are tentatively planned for July 23rd.
23rd. Yeah, so that next week after that, so go and do the Aerospace games, and then they can come and do that.
2 years.
What's that?
You missed 2 years.
Of the Aerospace games? Yeah. Yeah, so we have to do that. And then this is a list of our these 4 are the ones that were created by us in conjunction with a partnership with another company who helped us modify them, so that they're standard. And then we also use NASA resources. We printed them out and we use them, both in person and on Zoom. And then this one's really cool. If you haven't tried it yet, the Iss Docking Simulator. I fail every time, but I can spend like 2 hours doing it. That's it. Thank you. Do you have any other questions?
Interesting conjunction with that, one of the groups that I supported is called the Bridge Builders Foundation, which is intended to support those underserved communities and bring them, higher. And when we went to give this talk to the students, they were completely inspired. I mean, this is something that brings them completely out of the kind of box that they're used to and expand much beyond, what they would see normally. So
yeah, this is not in the books, let me tell you. And then just another side note, this last year I've been teaching science, natural disasters course at Cal State LA. It falls under the geology department for non-science majors. And I've been having a blast. And I noticed that when I was looking at the curriculum, it didn't have anything about asteroids. So I had to embed something. And so I use a lot of our resources that we've created for this to teach them. And I got really good reviews. The kids want more.
And so those resources, they require that we connect them with the next generation science standards, which are those standards that are published by California Board of Education. And this year or last year, they actually included planetary defense in those standards. It's quite amazing. So the basic physics is implemented through those standards, which was very good. So it's connected to what we do in a very straightforward way. So thank you very much.
Thank you.
Next. And do we need to switch a laptop for you, Phil? I guess.
Yeah, I got it. It's on my computer.
So you will do it?
Yeah. But let me remind you, Dr. Miller, this right now is 5. We're kind of 25 minutes behind.
Yeah.
So unless professor can extend it, we might try to speed it up.
Yeah, he said we can stay until midnight. No, we'll shoot for 5:30, and I will just adjust my talk to the minutes that left, maybe 5 minutes over or something like this, but I'm going to run very quickly. So I guess.
Okay. And do you have it, or do I need to plug in?
Oh, you can plug in, yeah.
I can plug in?
Oh, no, I think it's better because then you have to log into Zoom.
Oh, okay.
Yeah, you just
So
let me
just
know.
use this?
It's not on this computer.
Oh, it's not on
your
this
computer?
No, it's not. Okay, you have to plug it.
I know.
Just unplug it and plug it back in.
But then can you log in on Zoom as well? Because this way people online can see it.
I can't get Wi-Fi.
It's a Wi-Fi test, but it will take a few minutes though. I have it ready with the slides.
Oh, well, if you have my
I have the
presentation.
Yeah,
okay. You want to, can you click through it too? Yeah.
Oh, okay. It's there.
Yes, there was the Santa Monica.
So I can also leave it.
Temporary. You have the power tracking?
I have enough power for this.
Okay, awesome. Okay. Hi, I'm Bill Groves. I look like this. I'm the writer and producer of an IMAX movie called Asteroid Hunters. And it's basically a primer on how to protect our planet against asteroids. And it opens up, just in case you're curious, a week from tomorrow at the California Science Center. So this is perfect timing. So anyway, you know, I'm trying to save the planet like everybody else here, one movie at a time. And so there's basically 3 legs to the stool and using media to help protect our planet. And I'm going to go through those 3 points. The longest point is going to be the first one. That doesn't mean this is going to be long, don't worry. So anyway, so media, its role that it can play in helping make people aware of a problem and then give us ideas on how to fix it is really what my focus is. Go next slide. So the message. So asteroid impacts are one natural disaster we can actually prevent. Now, a lot of people don't know that. And I'll get into a little bit of the reasons on why that's the case. So why don't we go to the next slide?
Can you shrink the little box?
Oh, sorry.
You don't need it.
No.
Yeah, there you go. Yeah. Okay.
All right, so movies can be weapons of mass instruction. And so with that, though, is sort of a two-sided coin. Why don't we go to the next slide? So as with Greek theater, media has 2 phases, happy and sad. And we'll get into what that means. Next slide. Okay, so I went and tried to find any movie, any TV show that got into planetary defense. And the first one I found was a 1953 episode of Superman. And what I really love is that he's into deflection, not blowing the thing up, right? Which is probably a better idea. So I thought that was kind of cool. If you ever track down the episode, though, the asteroid makes Superman get amnesia and weird things like that. So, you know, they get a lot of things wrong, of course. But I found this to be really interesting. So next slide. Okay, so this is where we really go off the rails. Most films put the science in the back seat because it's all about the story. Their mission isn't really to educate everybody. Is to get them emotionally engaged in a story that's about a character who's trying to fight an internal conflict of some sort. The positive is that these movies, this one, Deep Impact, etc., they've gone some distance in making people aware that there's an issue. The downside is they tend to make people think that if there's ever an asteroid coming our way, we just have to kiss our ass goodbye because we don't have oil rig workers to send up to go blowing an asteroid up. So that's it. End of story. But of course, the good news is actually better than that. So this is the downside. By the way, in my movie, no oil rig workers were harmed in the making of that film. So I feel kind of good about that part. Next slide. Okay, so this is my film. And you know, and when I realized that about 12 years ago that this was an important topic that I didn't feel was getting enough attention in the world, I decided I had to make a movie about it. And before I made the movie, I had to fully understand the subject matter. And that came from talking to folks at Aerospace, folks at JPL and NASA, et cetera. And so I learned everything there was to learn about planetary defense and asteroids. And then I wrote the script. So I realized most documentaries tell you what is or what was. This movie has to tell you what could be, because it's all about anticipating a problem. And in order to make it a legitimate story and useful to an audience, we show real scientists so it conveys to the audience, this is not make-believe. One of the real scientists featured in the film, sitting right there, by the way, You don't know what he looks like because he's got this football on the front of his face. And we show the history of asteroids and the enormous timelines involved in the movement of asteroids. And they're actually spread out. They're not like a Star Wars film all clustered together. So, so it's to help us understand, when an asteroid might hit. And we certainly know it's not if, because it's just a question of when. And we show the science of an impact by using actual laws of physics and research that's come from examining craters and natural impacts and the physics involved in that. The great thing is about a movie, you don't have to say all the words, orbital mechanics and heat ablation and all this sort of stuff to convey these ideas, because you get to show them. And I'll in a moment get into how movies are really good at showing science so you get an intuitive understanding of it. And then we show that today's technology can actually do the job. So that's what the movie goes through. It shows you that here's the problem, here are the challenges, and here are the solutions. So that, and it doesn't do it by trying to scare the audience either, but it uses the power of cinema to engage the audience, to make them excited and interested, to dilate those pupils in that dark theater so that all that information goes right to the back of their skull and doesn't leave. Because you want them to be engaged, and we'll get into why you want them to be engaged in a moment or two. Next slide. So, what's the advantage of cinema? Well, just about everything that we learn around in the world around us comes from our eyes and ears. And the movies exploit that. And they go, with bright sound, big screens, so it occupies your field of vision. And also, high range of sound, highs and lows and stereo and surround and all this sort of stuff, so that you get as much of a visceral experience in watching that film. And the same thing goes with anything you watch on an IMAX screen. And when I made Asteroid Hunters, we certainly exploited all of those tools, that canvas. Next slide. So this is where movies are really good at sort of explaining science without ever actually explaining it. So we take advantage of our internal software. Evolution has given us the hard wiring to judge the world around us. And the visuals, sound effects, and the music boost emotion, which enhances our focus and memory and learning experience. So here's a tossed ball or object being pulled back down to Earth in gravity. These are the sorts of parabolic shapes that it makes. And there's all sorts of mathematical formulas that would tell you what to predict when something of a certain weight is given a certain velocity and where it should land. Movies take advantage of our innate ability to understand these things. How many of you can take a ball on one side, throw it, without even looking, know where to put your hand so it catches the ball? So we're really well designed to understanding sort of movement on the scale that involves asteroids. When you get into subatomic particles, they're kind of screwed, and then you really need the movies to understand that. So next slide. Okay, so the other advantage that movies have, we can make the abstract real. We can give shape and design and movement to things that are strictly in the imaginations of scientists. And so we play with scale, so you can speed up things that might take years and years and years to actually portray. So you can do all of these sorts of tricks so that you can convey the concept of a very complex idea and make it intuitive. Next slide. Okay, here's a great part about media too. It's autoerotic. It likes to talk about itself. It spreads itself out. When there's a movie out there, it'll use all sorts of other media to talk about the movie. And there's certain forms of leverage that come with that. In Asteroid Hunters, Daisy Ridley, the star of the last 3 Star Wars films, is the narrator of the film. So all the Daisy Ridley fans began digging up the articles. They see it, they post it in their social media. Next slide. So, when the Kennedy Space Center opened up a year and a half ago, all sorts of articles began springing up on the movie. So and even if someone didn't go to the movie, they start to become aware of this issue, which is really the objective of the film. Making money for IMAX is certainly one of the objectives, but that's sort of a nice sort of consequence of spreading the word and having people talk about this topic, because that's really the goal. That's really the reason I made the film. Next slide. And then this, this is an illustration of the social media. These are off a couple of my accounts, and I just grabbed a couple of them to illustrate that, these sorts of things that I talked about. A Daisy Ridley fan Instagram, that has a whole bunch of followers. She posted, or he, I don't know, posted it because Daisy Ridley's in the film, and he's a Daisy Ridley fan. And so, friends and family, the word gets spread that way as well. Next slide. And the great thing is that, movies reach all demographics. As I mentioned, that's playing at the Kennedy Space Center. And I talk to the people there all the time, and they're saying families are coming in, people ages 8 to 80 are seeing this film, and they're getting it, they're coming out, buzzing about the film, and they're talking about a subject matter that they never knew that there was a real concern, a real threat out there in space that might one day affect us. Next slide. Now, this part came recently. In February, by the way, this is one of my favorite slides, because this is a room full of people looking at an image of a room full of people looking at an image. As a filmmaker, I get sort of a secret pleasure out of that.
People online looking at an image.
Oh, yeah. Sort of doubling over, hey guys online. Put a mirror behind you and we might implode. So NASA and some of the other agencies like FEMA, Department of Defense, they had a tabletop exercise in February. And a tabletop exercise is when you take an imaginary asteroid that's following actual laws of physics and is destined to hit Earth, they anticipate. This is a growing percentage. It's sort of like one of those tornado cones or hurricane cones of probability, when they're going, well, it might hit us, it might miss, the Florida panhandle, who knows? And then, so they have to go through the exercise and develop policy on what they would do. And they recently used the impact sequence from my movie as a way of introducing some of the challenges to their scientists so that they can sharpen their policy ideas. And so, again, for me, this was great, having the movie sort of do some of the mission in the sort of higher levels of people's interest and activity on this subject is really gratifying, but more importantly, it's helpful. Next slide. And of course, the movie gets out there into the rest of the world. It's been playing in Europe and Asia. It's playing in Australia now. It's playing in, of course, in parts of North America. And it's going to increase in runs. The pandemic really sort of slowed things down with this movie. So you'll start to see it pop up around your friends and family cities, hopefully sometime in the next 6 months to a year or so. So why does informing the public matter? So that's when we get sort of the second leg of that three-legged stool. Next slide. Because the problem is money. Now, I don't know if you guys know about the NEO Surveyor mission. This is an important space telescope it's designed to park itself at Lagrange point 1, which is this neutral buoyancy spot in terms of gravitational influence between the Earth and the sun. And it's designed to put a space telescope there so that it has its back to the sun, so it can look at asteroids that are whizzing between the sun and the Earth, because seeing asteroids during the day is virtually impossible for many of the assets on the ground or in Earth orbit. So we need a space telescope. Well, the funding for the space telescope was just cut. So this space telescope is nowhere near getting off the ground for probably another 5 to 10 years. I'm hearing is the estimate, which is really a shame. So money is a crucial ingredient. So how do we fix that problem? Next slide. Well, the money comes from here is a big hint. This is a big clue. This is our Congress. They hold the purse strings for this country anyway. And the United States is the leader of the globe when it comes to planetary defense. So, that's whether we like the job or not, it's ours. Next slide. So how do we get their attention? Now, if you've seen Independence Day, I'm not suggesting we blow up the White House. It gets tempting every once in a while. Next slide. We threaten no jobs, though. That's what we can do. So if we have an educated electorate, then they can start to make Congress care more. And maybe when it gets time to deciding the budget on that space telescope, they go, oh, you know, I kind of want to get re-elected next election. So maybe we should make this worthwhile and put some money into it. So so that's how we get to them. And so this is sort of a wash, rinse, repeat sort of process. So next slide. So you go back to message one, and you just keep drumming it in to the people, so the people can elect the officials that know that we have a populace that understands this issue and that cares about it, which makes them care about it. Whatever the mind of man can conceive and believe, it can achieve. This is some guy that was like a self-help guru of the 1930s of last century. Next slide. And that's really the message. Thank you. I may have answered all the questions, but I don't know. Yes.
How did you feel about like Don't Look Up?
Feel that what?
About the movie Don't Look Up? Because that was a asteroid coming to Earth. I don't know if you saw that.
Sorry, what was
Don't Look Up.
Don't Look Up.
The new movie.
Oh, Don't Look Up. Oh, the Netflix film. What do I think about it?
Yeah, just like
I found it kind of annoying, actually. They had they have a greater emphasis on telling a story, and their genre of film in this was satire. So they were trying to go for more laughs. I kind of think they partially succeeded, versus giving you a grounded, real world idea of how it works. And one of the three characters with Leonardo DiCaprio and Jennifer Lawrence, the guy that was always with them was the Planetary Defense Officer. Well, there's only one of those in the world right now. And so far, there's only one of them that have ever existed, and I know him. And this guy was no Planetary Defense Officer. Anything else? Awesome. Great. Thanks.
Thank you, Phil.
Thanks, Ken.
This one. All right. So thank you. I'm going to thank you. I'm going to do title. How do you say surfing, right? I'm going to just go through a series of web pages and small, just the title of things that we have done because of the shortage of time. We might have just a few minutes over, but I'll try to make it near time.
Can you share on Zoom?
Oh, share on Zoom. Okay, yeah. Let's see.
Great.
Oh, yeah.
That's it. This one, huh?
Yeah, that's right.
Are we good?
Good.
Okay. All right, so well. Okay. So what I'm going to do here quickly is just go over some of the studies that we've done. And recently, partly because of COVID and partly because of the general process that we have, is that any new material that we have to release for public viewing by Aerospace goes through a very lengthy review process. And I was told that if I can use web pages, live web pages that anybody can just go and access, it's free to use. I don't need to clear anything there. So my presentations are now using materials that had been cleared in combination of live web pages. Anybody can go and visit those pages or go and download those materials from conferences, publications, and so on and so forth. So this is for today. And we have conducted a study a few years ago, which I called Planetary Defense Far and Near. Far meaning it's in deep space, near it's near the surface of our planet. I'm going to skip most of that here. Here is some of this presentation, which explains that if we have years to decades, yeah, we can go with the usual process, build the system, test the system, launch them, and hopefully do what Psyche is doing, do what those missions that are going to visit those other planets in 10 or 15 years. All of that is a standard thing that we can do. But if we have months to years, the only possible option is that we have pre-built system that is on the path, ready to go. We don't have it today. That's a gap. And what do we do if we have minutes to months? I think it was mentioned earlier, the Chelyabinsk case from 9 years ago, things like that. Can we do something about that? So this was the heart of this presentation. And I think what I'm going to do here, I'm going to jump quickly to a few web pages so we can see what's going on a little bit more up to date. And this will be, I believe, here. Yeah, okay. So, all right. So this event is in commemoration or part of the Asteroid Day movement. This is their page. This is the countdown to the time to June 30th. Go visit their page. They organize thousands of local events, talks, classes, and so on and so forth. So this is what this event is all about. This is the NASA Planetary Defense page. It gives wealth of information about their missions, including Psyche, and I'm not sure about the budgets that get cut or not cut, but they give good wealth of overview for all of the missions and definitions of what planetary defense is. For those that don't know what it is, it's an excellent place to go visit. Aerospace also has a page, which we created about a year and a half ago to do the teaming exercises that we explained earlier. And this page encompasses some of the activities that we do. For example, Monica talked about those teaching aids. So we have a link here that you can go to those lesson plans and the connections with the science standards. All of that is in this link here. We also have a link to the trailer of the movie, which Phil talked about. So this gives about 1.5 minutes excerpts from the movie. And by the way, Phil, I am in your movie, but we have another participant, which is Ben. Ben here is my colleague, and he stuck with me for the duration of this day. So we have two people from Aerospace that are in your movie here, right here in this room.
We have to get your autographs.
And then also, we talked about the app, which I explained during Monica's presentation. This is where you can get some demo of the app and information how it works and what goes behind the app. We also use different techniques. For example, some of our guys use artificial intelligence to look in archival pictures of the night sky to extract, to discover asteroids that were not discovered by either human or other machine techniques. So this is the study that they've done, one of them. And of course, in the benefit of inspiring the next generation of scientists and engineers, this is a paper that me and my son wrote together a few years ago when he was transitioning from high school to college. None of us knew what we are doing, but we generated the paper. And this paper is a fun paper to do. We already have 2 more papers that we generated together. And so part of this kind of father and son bonding is, I think, a wonderful way to inspire the next generation of scientists and engineers. All of this is on the Aerospace website. So let's just see what goes on around our neighborhood. This is a picture of NASA's Juno mission of Ganymede. And you can see that this moon of Jupiter is littered with impact craters. I'm sure that a lot of you have visited a telescope that looked at the moon and saw the abundance of impact craters on the moon. Sometimes they are nested one within each other. The moon was completely bombarded with asteroids, and we are in the same neighborhood, right? The moon and us are in the very same neighborhood. We don't see it on the Earth because of geological activities that tend to erase this evidence, but it does exist. What actually does impact with us? These are called bolides and fireballs. These are small objects. They were shown in the morning. And this is the JPL page, which keeps track of those objects, which you can have on. This one is the one that occurred 9 years ago. And in the last 3 decades, they had how many? 917. All of these are the actual impacts with our planet that happen to be small enough to either not be detected, not cause damage. Occasionally, they did cause some damage, especially the red one here is an object that caused damage, and it inspired the study I described at the beginning of my talk, in my mind at least. These are just a few Wikipedia pages. This is where I'm going to do title surfing. Here is an overall count of known impact craters on the Earth. Here is the page that talks about the impact that caused the extinction of the dinosaurs. It has wealth of references at the bottom of the page. I encourage you to go and visit those pages or just Google those topics and read about those topics. Here is the page about meteor craters. So it's in our neighboring state of Arizona. Any of you has been to meteor crater, by the way? Oh, quite a few of you. Anybody has been to the bottom of the crater? So I was sitting at our Planetary Defense Conference, which was in Romania in 2011. And we were trying to find the next location for the conference. At that time, our family did a trip to Meteor Crater, and we said, this is a fantastic location for our next conference. And we accepted it. And so the next conference took at the city of Flagstaff, which is about half an hour from the crater. And we were given a tour to the bottom of the crater by a renowned geologist that studied those layer inversions dynamics that occur during an impact. Fascinating tour. So if you are planning a tour to the Grand Canyon, which I'm sure that all of you are, it's in the same neighborhood. Take a few hours to and go visit Meteor Crater and have a fantastic visitor center. And it's a beautiful occasion. Very recently, a friend of our neighbor passed by and we talked casually about things. And she said, you know that in an island that belongs to Estonia, there are a few small impact craters. This was completely new to me. I Googled and sure enough, there are several impact craters, very small ones, unknown. And now it makes you want to go and visit Estonia. Tunguska. Tunguska is the event that occurred in the year 1908. It inspired the Asteroid Day advocacy organization. And today, it's an event that occurred over Russia. And it leveled about 2,000 square kilometers of Siberian forest. And it was a concern because an explosion like this, which was undetected, that would have occurred over any major city around the globe would incinerate the city instantly. Millions would perish instantly. And we have no protection. It is very, very far in between. But if it happens, it could be a very bad day somewhere. This is part of the wake-up awareness and understanding that we want to do something about this hazard, which is relatively new hazard. Right? Only the last 2 or 3 decades is when we realized that this is something that could change life on Earth. Here's something that earlier, I think Alan said, oh yeah, there are several studies that talked about objects that behave like Tunguska and change civilization on Earth. I'm not going to challenge anything. It's a serious study from the University of Santa Barbara. And it occurred in the area where I grew up, right, Israel. So here is the area where it occurred, and they found that this area was, let's see what was the before and after of it. So this is the before and after. They think that it looked like that in those old days, roughly speaking. This is how it looks today. And the way they concluded that this was created by a cosmic explosion is because they found those crystallized pieces that can only be formed in very high temperatures. And 3,500 years ago, there was no technology that could create those kind of crystallized materials out of the rocks. They exist in abundance in this area. They concluded it could only have happened because of cosmic object that perhaps affected civilization that existed back then and eliminated it off the ground. So who knows? Definitely it's a possibility. And here is where I'm going to fall into some problem here.
You can move the bar down.
Down well?
You can just take the bar down.
For this?
Yes.
If you click on the, and you can say hide floating meeting controls.
Further down.
One more down. Yep. Then they're gone.
All right.
That one you can move over.
That one I have no idea about. Okay.
Chelyabinsk is the event that occurred 9 years ago, where a small asteroid impacted the city of Chelyabinsk. It did not impact the city, it exploded over the city of Chelyabinsk. And I'm going to show a couple of very interesting videos because that event occurred just 2 months before our conference. So the conference was focused on this event. And scientists from Sandia and Lawrence Livermore created all kinds of simulations that told us what had happened and what could have happened. And that was the moment when some ideas sparked into my mind when I was watching those videos. I'm going to show them. So let's just skip this one. Okay, reality check was already shown in the morning, I think, where JPL maintains a page that is updated daily to see what's going on around our planet as we speak. And this is the page for today. They had one for the 18, which is now gone from this table here. But looking forward, you can see that there is a wealth of objects here that are making very close approach with our planet, essentially today, tomorrow, in the next few days. As an example, I looked at it, and here's an object which is about the size of Chelyabinsk to Tunguska, about somewhere in between those two, which is it's going to make a very close approach, 0.005 astronomical units, which is just a few lunar distances from us, which is considered very close to our neighborhood, and that's going to occur June 25th. How many of these are there? How many objects do exist as of today? That would be the next page. As of today, let's update it and see exactly. So by June 16, today is what, 18, right? So as of 2 days ago, we are aware of 29,000, over 29,000 objects. And the rate of discovery is obviously accelerating. With more telescopes being put into the sky, we find more and more and more. It is now understood that it probably will take a few decades to find all of these objects. We really live in the dark ages as of knowing what's out there, and we don't know what could come one day and hit us in the next 2 or 3 decades until we find all of them and can plan to respond if we find one that is aimed at the Earth. Right? So this is just a reality check for our planet. Now let's see how do I think of this? Huh? There is a way to move to the next step. I don't know what it is.
Yeah, you have to drag the whole
box
browser down. Yeah, try to grab it. Yeah.
Oh, okay. Okay. Thank you. JPL. Okay. JPL. Here is an asteroid that is called the Halloween asteroid. Why is it called the Halloween asteroid? It was discovered in 2015, 3 weeks before the passage of this asteroid over the Earth at a distance of about 1 lunar distance from us. And that is quite alarming. This asteroid is about 600 meters in diameter, at about 1.3 lunar distance from us, and it came at a tremendous speed. It came at around 35 kilometers per second, which is about 2 to 3 times faster than typical asteroids. And so the question was, what would happen if this asteroid were aimed at the Earth and you were told that in 3 weeks you have to evacuate North America, Europe, Africa, because this continent would have been destroyed by that kind of object? It's an alarming situation. It's a real hazard that we are faced, very, very low probability, but the consequences could be severe. So that's why we want to do something about that. We want to be able to address this because we have the technology to attempt something against those kind of situations. Right? That's what you're trying to do. Okay, Psyche. We talked about Psyche. This is where the science comes in. Right? First of all, we need to understand what these objects are made out of. How do we actually reach out to an object, change those orbital planes, do kind of operations next to asteroids? Because anything that we do with asteroids will involve some engineering, some guidance and technology. We have to understand this. And this is, even if that particular mission is science focused, has a lot of the know-how that would be applied to any asteroid mitigation mission. Okay, NeoSurveyor, it might suffer some budgetary delays. That could be. Hopefully, within those delays, nothing big would happen because those events are definitely far in between. But the effort is definitely building. The momentum is building out there to do something about it. Even if delays occur, it's part of the reality in which we live. We have to compete with many other priorities that exist in our world today. Some of them are very, very immediate. So we cannot throw the bank at an asteroid when we have other things that are going on that needs immediate attention. But again, this is the excellent page to go and visit. It's the Planetary Society page. It explains what this mission is doing. And the idea here is to use infrared sensors to look at the back of the asteroid, which is illuminated by the sun, and either give us an earlier alert as to something that might come to our way in a day or a week, and we can do evacuations, or simply discover them a few orbits before their impact, right? If they can tell us, okay, in 3 or 4 orbits of this object, it's going to aim at the Earth. And we can now try to do something about it, perhaps destroy it, deflect it, whatever could be possible. This mission is going to help out with that. Plus, it's going to help with discovery of a lot more of these objects than the rate of discovery is today. Okay, let me move forward quickly in the benefit of time. Now, it was a mission that was discovered in the morning. I'm not going to go into this any more than was discovered, but that's going to be all in the news at the end of September, where we are going to see whether it was successful or not, right? We want to know, we wish it would be successful, but we definitely want to know if it didn't meet the objective, because we might have a bigger gap than we think in addressing those kind of threats, right? So hopefully it will be good news, but if not, we need to learn how to do it better next time to learn from this mission and other missions that might occur. We put it all together in those planetary defense conferences that we organize every other year. We had one last year in April. It was intended to be held in person in Vienna, but because of COVID, it was held virtually. The next one is planned again in Vienna, in person. So far it looks good, and the plan is to hold it in person. Anybody who wants to contribute to that is welcome. The abstract submission is going to be in around the October-November timeframe, and the paper is probably around February-March of next year. Anybody who wants to contribute, to get involved, think about getting involved with this project. The conference itself is fully recorded, so you can read the conference report, you can go to the program, and if you go to the program, so you can watch the entire conference. It was fully recorded. You can get each presentation materials and read about what was presented on each one of those topics every single day. So we are going to repeat the same standard for the next conference next year. Aerospace. So this is the page that Aerospace created to do asteroid deflection competitions. It gives a basic background about those asteroids, and if you click on the Aerospace app here, it's going to load the app. There is no programming skills that are required. There is no training that is required. You can just hit it code, and we found that those high school students pick it up so quickly that within minutes they can start competing on simple scenarios. And so we just turn off this knob here, and we can now try to deflect an asteroid away from this location here. I'm going to do a very, very quick demo. Let me turn it off because it's simpler. So here is a scenario where we start with the PDC 19, the Planetary Defense Conference 19 object. There is a list of about a couple of dozen of these. Each of these objects have different orbits. They present different challenges of orbital mechanics deflection. So turns out not orbits were born the same. Each orbit presents different type of difficulties to address and different geometry. So all of this is encapsulated into this app. You pick one of these, it's going to load the orbits of the asteroid and the orbit of the Earth and those distances. And my job is to move this dot outside of the red circle. I'm going to do it by going to the page where I can use some launch vehicles, and we have 4 of them modeled here right now. And I'm going to try to change the mission design parameters, right? As I change the mission design parameters, I basically change the respective location of these objects in the respective orbits. Now we have a solution. That is the transfer trajectory, and I was able to move it, the object from the red dot to the green dot. That's not enough, right? Because somebody is going to complain, right? Why did you move it from your backyard to my backyard, right? So we don't want to have that happening, right? So we try to do that as much as we can here, and I can try to move it until probably a local maximum. I can try to move this one here, and I was able to find just a very small distance here. So this is done with launch vehicle performance in the tool, with the orbital mechanics embedded in the tool, partly generated by JPL, partly generated by Aerospace. It's a collaborative project. And so by turning on the team mode here, we can measure the performance metric here. We pre-calculated those deflection possibilities in those deflection maps. You can see that there are thousands of combinations of mission design parameters here that are very difficult to pick up in a kind of a contest scenario, right? I mean, we can always write a tool that will wrap itself up around this tool and give us the optimal solution. But we don't want to do that, right? That's something that any engineer could do. We want to create a contest in which the students engage and by trial and error try to find the best solution, and they do. They do, and we have those solutions. This creates thousands of possibilities for performance metrics, and it's a nice activity for about an hour with those students. And here is one that I gave recently in person in a local high school in Los Angeles, where the students were delighted to win some of those competitions. And a couple of them came to me and said, I'm going to be an aerospace engineer, which I think to me it's a mission success. Going back to this presentation, let me quickly jump back to what I've shown there, because we have a couple of nice clips. So, okay, so now I'm going to jump quickly to that I already gave. I mean, do you want to see this quick movie about jelly beans? Do we have 24 minutes still? It's okay?
Sure. Yeah.
Okay, so let's just watch it because I think it's really nice.
What exploded over Russia? Presented by Science at NASA. When the sun rose over Russia's Ural Mountains on Friday, February 15th, many residents of nearby Chelyabinsk already knew that a space rock was coming. Later that day, an asteroid named 2012 DA14 would pass by Earth only 17,200 miles above Indonesia. There was no danger of a collision, NASA assured the public. Maybe that's why, when the morning sky lit up with a second sun and a shockwave shattered windows in hundreds of buildings around Chelyabinsk, only a few people picking themselves off the ground figured it out right away. This was not a crashing plane or a rocket attack. It was a meteor strike, the most powerful since the Tunguska event of 1908, says Bill Cook of NASA's Meteoroid Environment Office. In a 1 in a million coincidence that still has NASA experts shaking their heads, a small asteroid completely unrelated to 2012 DA14 struck Earth only hours before the publicized event. These are rare events, and it is incredible to see them happening on the same day, says Paul Chodas of NASA's Near-Earth Object Program at JPL. Researchers have since pieced together what happened. The most telling information came from a network of infrasound sensors operated by the Comprehensive Test Ban Treaty Organization. Their purpose is to monitor nuclear explosions. Infrasound is a type of very low-frequency sound wave that only elephants, homing pigeons, and a few other animals can hear. It turns out that meteors entering Earth's atmosphere cause ripples of infrasound to spread through the air of our planet. By analyzing infrasound records, it is possible to learn how long a meteor was in the air, which direction it traveled, and how much energy it unleashed. The Russian meteor's infrasound signal was detected by multiple stations, including one in Alaska more than 6,500 kilometers from Chelyabinsk. Western Ontario professor of physics Peter Brown analyzed the data. The asteroid was about 17 meters in diameter and weighed approximately 10,000 metric tons, he reports. It struck Earth's atmosphere at 40,000 miles per hour and broke apart about 12 to 15 miles above Earth's surface. The energy of the resulting explosion exceeded 470 kilotons of TNT. For comparison, the first atomic bombs produced only 15 to 20 kilotons. Based on the trajectory of the fireball, analysts have also plotted its orbit. It originally came from the Asteroid Belt, about 2.5 times farther from the Sun than Earth, says Cook. Comparing the orbit of the Russian meteor to that of 2012 DA14, NASA orbit analysts have shown that there is no connection between the two. These are independent objects, Cook says. The fact that they reached Earth on the same day, one just a little closer than the other, appears to be a complete coincidence. Infrasound records confirm that the meteor entered the atmosphere at a shallow angle of about 20 degrees and lasted more than 30 seconds before it exploded. The loud report, which was heard and felt for hundreds of miles, marked the beginning of a scientific scavenger hunt. Thousands of fragments of the meteor are now scattered across the Ural countryside, and a small fraction have already been found. Preliminary reports, mainly communicated through the media, suggest that the asteroid was made mostly of stone with a bit of iron. In other words, a typical asteroid from beyond the orbit of Mars, says Cook. There are millions more just like it. And that is something to think about as the cleanup in Chelyabinsk continues. For more news about things coming out of the blue, visit science.net.
So the couple of things that stayed with me from this clip is that it wasn't a rocket attack. Imagine this event occurred today in Ukraine. Could it be misinterpreted as something different? Who knows? That's some of those risks of knowing what's going on out there. Second, there are millions of these that are still out there to be discovered. This page was prepared in 2018, and there were 18,000. Today, we saw that there are over 29,000. We are still in the discovery mode of those objects, very, very far behind others. So this is what I prepared back then. I'm going to skip most of it here and now. When I was at the conference, there was a guy from Sandia that presented those two simulations. So the asteroid entered at about 20 degrees, shallow entry, and he created a simulation of the actual asteroid. So if I click on that, it's going to show what it did. This is a simulation, a fully physics-based simulation of the asteroid. The energy was released at about 20 to 30 kilometers, and the shockwave that occurred was whatever it was. But the more typical case is when those asteroids hit at a steeper angle. So he set it up to maybe around 60 degrees or so, and that is what it would have done. So it would have released its energy at much lower altitude and caused much more severe damage on the ground probably kill thousands of people, destroy most of the buildings, and a small asteroid like this, which was ignored and up until this point, turns out to be, it could be a major risk. And this kind of event is a twice a century type of thing. So it could happen in our lifetime. That is where things could actually hit our, well-being. Something has to be done. So I was sitting at the conference, and I was thinking, if we had a way to intercept those asteroids just at a slightly higher altitude, we could save the day over one of those cities by simply breaking them out into small fragments that will burn in the atmosphere at a higher altitude. Could we do that? So we started a study in which we said, well, if we can shoot those ballistic missiles, can we use the same technology to shoot out those asteroids? That was the heart of the study. So first of all, it was the intercept part. Second was, can we actually break those asteroids? And the third, can we reduce the damage on the ground? This is future work, basically. We're going to skip the majority. There is a whole system that will have to be designed here. Here is the famous plot. And I'm going to skip all of this. I think there was a question earlier about the distribution of those asteroids. I think you asked there. And it turns out about 8% of those metallics kind, 17% of the stone asteroids, and the rest are more like other pile type of things. We focused on the S type because it is perceived that this is what the asteroid was probably made out of, this stony material. And we ran hydrocode analysis on this type of asteroid. I'll show you in a minute. We did a system design that takes into account some radar system that continuously scans the sky, discover them, create a firing solution, launches a kill vehicle within seconds, and intercept the object literally minutes before it explodes on the ground. We will need to develop probably dedicated sensors for that. We will have to develop ground systems and so on and so forth. The basic idea is that if we did nothing, the initial breakup would have occurred at a low altitude, destroy a key installation or inhabited area. We would like to intercept it earlier at higher altitude such that we can essentially increase the surface area of this object and let atmosphere do the job for us, basically at a higher altitude. Yeah, okay, let me just jump over a few of these things. So we used some analysis to find how much energy do we need to actually break it based on those studies that are here. And by doing that, we ran a hydrocode. These are the parameters of the actual object. These are the parameters that we use in the simulation. We use dunite, representing solid rock, with density of 3, roughly similar parameters to that. And we ran several cases where we used one kill vehicle, larger vehicle, multiple smaller vehicles, some kill vehicles with explosive materials. And so by running those simulations, we showed what could happen. So this is when a ton of kill vehicle runs into this asteroid. We actually found that it's not that the kill vehicle runs into the asteroid, it's the asteroid that runs into the kill vehicle. It's much, much faster than the kill vehicle itself. So this creates big questions about timing and fusing. All of these are engineering questions that we basically ignore to just find if the basic physics is in there, it doesn't violate any fundamental principle laws of physics. So this is one, we tried a big one here, 5 ton, and the 5 ton actually did the job. So we completely decimated this object. That is a solution, but can we launch a 5 ton, payload in zero warning essentially? Maybe, maybe not. If not, then maybe we can launch 5 smaller ones like this. So here is 1, 2, 3, 4, 5. Yeah, it knocked it out, basically destroyed the object. But what if we add explosive, just standard explosive, nothing nuclear here, just standard explosive, 1 and 2. So 1 and 2, we found that 1 and 2, most of the pressure escaped outside, didn't do the job really. So let's try 2 and 3. So 2 and 3, 1, 2, oops. so this 123. Let's see. This is 4, actually. 4 was kind of more of an overkill. I think the previous one was the 1 to 3. So, yeah, 1 to 3. So 1 to 3 did the job. So if you combine explosive with 3 kill vehicles, we can actually destroy the Chelyabinsk object. So that was a good finding, and I think basically, and then the rest of it was a bunch of Monte Carlo runs. Oh, so this is a nice video. It shows that we can actually intercept it. So here is a physics simulation. It shows the launch vehicle as it launches in time to do the job. Here is the end of the boost phase. Now it's crossing through space for collision with the asteroid, which approaches the Earth. And just to make sure, we also launched a second mission here. Here's another launch vehicle that also have a intercept solution. And so we have 2 attempts. And we can see here that at some point the asteroid will approach the kill vehicle and we have an intercept. So we solved 2 of the problems. We showed that we can intercept them in principle, of course, right? And we can actually destroy those vehicles. We didn't do the analysis of how much of the impact on the ground is going to be eliminated, but NASA Ames is busy doing something like that. So there are several organizations that are looking into this type of solutions. And and this is just a nice illustration showing that because those asteroids can approach from a random direction, we should be able to have a system. This is a single system in the center of US that can respond to any random direction of an asteroid if it was discovered within an hour before impact. And an hour before impact is very, very close. If we create smaller systems that are distributed in regional, we can knock those asteroids down even if they're discovered at like 15 minutes before impact, which is amazing. And it's going to occur at 1,000 kilometers altitude, which is a fantastic altitude. Break them away. Looks like a little bit of a computer game. It excites the students and you say, who would like to design this computer game? So this is all physics based. Basic physics. There is nothing high-tech GNC in here or anything like that. That's all big issues that could be solved, but will require a lot more funding. But basic physics is there. So we can do something. The point here is that we can actually do something about those problems. So, okay, so I think we just keep all kind of future hopes kind of thing that we plan to do. And yeah, that's it. And now I'm going to switch back to screen sharing is stopped. This. Should be sharing or should I avoid them? Thank you. Okay, so just last couple of things. Part of the Planetary Defense Conferences that we hold every other year is an exercise that is designed to practice the whole process of discovering an object, going through the characterization, mission design, policy, legal, whatever is involved with a real scenario is practiced during that conference. Realistic scenarios computed by JPL and designed by other organizations. Lawrence Livermore does the impact analysis, Goddard does the mission design, JPL do the orbit design, and it all put together into those different scenarios here that is being exercised every conference. I'm going to mention just one, which is a particularly interesting one, which is 2019 comet scenario. So this is a simulated comet scenario. Comets objects that come from the outer regions of the solar system. They are discovered very late. They are usually bigger than an average asteroid. They come at a much faster speed because they come from a higher altitude. And they could come at a declination of much outside of the ecliptic plane. So you just don't, you cannot launch a rocket and do a plane change at a short time to go way above the ecliptic plane. It's impossible to, rockets just cannot do that. So we did a quick study to that particular one, which was presumed to have no solution, but we found a solution. So this is the paper that we put together for the Planetary Defense Conference 19, and it was basically trying to find a solution for this conference, for this comet problem. We tried our tool initially, and we found that we cannot deflect this object because the rocket would intercept with the comet about 2 to 3 weeks before impact. This is the best we could do with a chemical rocket. We attempted to launch 30 NASA SLS rockets, which are the heaviest rockets that are just about to come on board, and we were able to move the object from here to here. That's no solution, right? And it's impractical, infeasible, impossible. What can we do? So turns out that we can actually employ solar cell technology to launch a small spacecraft with a very high area to mass ratio towards the sun and use the solar radiation pressure to do the plane change for a much, much earlier intercept of the spacecraft with the approaching comet and do the whole operation in deep space rather than when it's almost at collision with a planet. So we found that that particular technology, I'm going to show a video in just a moment. It looks like that when it is deployed. It looks like this when it is compacted into the launch vehicle. When it is deployed, those solar veins are steerable, so they can optimize the amount of orbit modification that is needed to do that. So all of that is a feasible solution if we can obtain 100-to-1 area to mass ratio. And modern materials suggest that it is within reach. And this is the simulation that we've done. Let me play it quickly, and this will basically wrap it all up, just to show some of the things that we do. So this would be this one here. So this is again physics-based simulation with orbital mechanics basically in the loop here. And what we see here is an initial launch ingressing towards the sun using solar radiation to change the plane of the orbit over several revolutions, purely using solar veins, steerable solar veins. When we achieved the intercept plane, we then switch to spiraling out on an intercept trajectory, which will rise and meet with the approaching comet in a few seconds. So all of that is just basic orbital mechanics behind the physics of solar radiation effect on the spacecraft. We can do that. We can do something that chemical rockets just cannot do. So now the spacecraft that could have perhaps a nuclear device on board approach the object and intercept it at about 3 astronomical units from the Earth, which is very safe to explode anything, and hopefully just eliminate the threat. So some nice study that we've done here. All of these are initial studies that are done, those sort of like fun hobby studies. And lastly, so anybody heard about this company, Spin Launch? Spin Launch is a company that proposes to launch satellites, small payloads to space using this evacuated centrifuge they are experimenting now in Optical, and they're planning to do a test, I think, end of this year, that is funded by NASA. And eventually they want actually to launch to orbit. And we are starting a small study to see, can we use this kind of device to deflect asteroids? That's a current thing that is ongoing, and numbers suggest that it is possible. So I think with that, I am basically done. Yeah, okay. With that, I'm concluding the event. Are there any? Is there any time for a question or?
Have you read Arthur C. Clarke's Rendezvous with Rama?
Part of it, yeah, many years ago.
You realize that he predicts that your system will be funded right after a major city is lost in the world.
Yeah.
That was his prediction.
Yeah, no doubt that we have to have those awareness-raising singular events. Some of it is events that occur in recent times, and some of them come through research and observation. Tunguska, medium crater, Shoemaker-Levy, right? The Shoemaker-Levy was a wake-up event because they said in a comet that broke into about 21 large pieces would have put Earth in the address book, we wouldn't be here today. We would not be here. That's just the reality, and it's a real thing. So, can it happen to us? With tiny probability, yes. It can happen to us in 5 minutes. The likelihood, tiny. And that's why when we approach those people who can write checks, they say, when can it happen? It can happen between now and 100 years. I said, please go. So that's where we are today. Any questions? I'm sorry about a few minutes late, but I hope that I gave the message. Yes.
You know, you showed the composition of the asteroid. Does it make a difference in the composition as to the size of the explosion when it, like in the Tunguska thing? Would it, if it was a different composition, would it be a different level of explosion?
I think so. It's not my expertise, but I believe that if a object is made out of, is like a rubber pipe of aggregated pieces, essentially it's going to disintegrate higher in the altitude. It's the same amount of energy, right? Same amount of energy that is dependent on the mass, but it's going to disperse at a higher altitude and perhaps dilute the effect on the ground more efficiently than a metallic, like the meteor crater case, where it was a single object that acted more like a bullet penetrating through the atmosphere and hitting the ground, creating that. So I think the jury is out. You might know a little bit more.
I agree with you. I think it depends on almost all stony meteorites break up in the atmosphere.
Would that mean that the metal one would be the worst?
Possibly, but
I think from what I heard is that if an object makes it down to the ground, it creates a larger localized damage.
Right.
If the object explodes in the atmosphere, it creates a shock wave that could affect much wider area, maybe less of a devastation, but much wider area. So if you're talking about a city, it doesn't matter if you were killed by, you know, a localized object or by something that exploded in the atmosphere, except it's going to affect much wider area than localized. Depending on the size as well, right? Bigger objects will act like a bullet either way, right? It's going to lose some of its material and atmospheric entry, but when you're talking about a 10-kilometer object, that part of it hits the ground and part of it hasn't entered the atmosphere yet.
Yeah, and let me just say that, you know, having studied explosions, physiological effects on people, which we seem to forget, is that the first physiological effect that is harmful is eardrum bursting. And that did not happen in Russia, but having a large area where every person has their eardrums burst is not a good thing.
It is not. And I think there are some simulations that show that what I've done a few years ago, I took that Halloween asteroid that I showed earlier, the 600 meters, and I placed it into a simulation that was created by Purdue University, and I placed myself at 100 kilometers away from the epicenter. If that asteroid had impacted in the ocean, not too far in the ocean, but near the shoreline, it would have created tidal waves of 120 feet high at the shore, which will extend miles inland and basically wash everything clean into the ocean. And most of the world communities live on the shorelines, right? It would have cleaned a big area along the shoreline. If the object had impacted in the ground, then 100 kilometers away from the epicenter, it would cause building collapse, third-degree burns, and so on and so forth, which means that this is a continental scale devastation. And it's a real object that just happened to miss us by one lunar distance. What was it, 7 years ago, right? Something like that. And the Chernobyl shows that two objects that were perceived to not occur on the same day did occur on the very same day. One of them actually did an impact. The other one was just very close approach. So you never know, right? Sometimes those confluence of things can surprise you. So the key message is that we do have the technology to attempt to do something about it. And I'm not claiming that we have to throw the bank at planetary defense. That won't do because most likely it will never get used. But over time, we want to put emphasis on discovery, right? Let's first discover them, know what's out there. This is where the majority of the effort is going on today. And then if we find something that deserves more attention because it has higher than comfortable chance of impact, let's see what we can do about it. But hopefully over a few decades, we know the majority of these objects. We'll be able to predict them a few decades in advance, build those systems that will do something about it. And part of it is the study that we are doing now is try to build a concept that will address it decades in advance.
There's an online question about tether. Do you have one more question?
About what?
I mean, there's a question about using tether for the. Do you have time?
Yeah, well.
Okay, Holger, go ahead.
I was wondering if conductive tethers were considered to change the orbit. Conductive tethers are considered to lower orbits of low Earth or to deorbit satellites in low Earth orbit. And if those conductive tethers are also considered for asteroid deflection.
So I can answer it in a different direction. So we did a couple of studies where we looked at using not conductive tether, but just a very long space tether with a balancing mass at the other end to do sort of like a swing, like a, how do you call it, a flyby or a swing by, using a tethered swing by. Basically, create two masses, one of is the asteroid, the other one is a balancing mass, and swing one against the other to modify the trajectory of the asteroid. And we've shown that you can do that. If you can capture, you have a capturing device at the end of a long tether, which could be thousands of kilometers, by the way, and make it such that you time it such that it grabs onto the asteroid at the right place in the orbit, then just the dynamics of these two objects acting together over time is going to modify the orbit of the asteroid such that it will move it away from the Earth. That's conceptually possible. But I don't think that using electric tethers is anything that has been conceived feasible because this occurs in low Earth orbit, it interacts with the magnetic field of the Earth. That's way too late to do anything for any object that can cause damage, right? So I don't think that has been done. To my knowledge, it hasn't been addressed. So,
yeah, could be that the interplanetary magnetic field is too weak compared to Earth's magnetic field. And
also, it's very late in the game to handle it. I mean, you can attempt to do something like intercept it with ballistic missiles of those ballistic, but to deal with it with space shuttles is perhaps something to do dynamically in deep space, but not near Earth.
Yeah, thank you.
Sure, thank you. So thank you, everyone. Thank you for hosting us today here.
Thanks for coming, everyone. And,
Thank you, Professor.
yeah. So in case an asteroid doesn't hit tonight, be careful. Be careful on the freeway.